Good afternoon, everybody. My name is Dave Patino. This is Michael Chapa. This is Abdul Nazal, and we are the Team Space Capitals. Today, we're presenting our NASA contact sampling device that we've been working for 2 semesters. So for mission connection background, we're going to go over our agenda for today. We have 6 stuff. Consists of the project goal summary, criteria constraints, research and conceptual design, modeling and analysis, prototype development, testing, and potential future work. So for our project goal summary, it consisted of NASA is preparing to go to the lunar South Pole. Astronauts will collect a variety of geological lunar samples. They need a tool to help them complete this task. The objective is to gather undisturbed lunar regolith samples from to facilitate in-depth research into various aspects such as grain size and material variety up on the moon. Some safety requirements that were given to us consisted of 6, but us as in particular that we took into account for were the no sharp edges, no sharp points, no pinch points, and any hazardous points should be labeled as do not touch zones. So for material requirements, it was pretty simple. It had 2 requirements, which consisted of any material that we use for our device should be part of the neutral buoyancy lab guideline list, and any 3D printed components should have an infill of 75% or more. Last but not least, obviously our device has to function. Some that we took into account for as a team was consisted of the 1 to 5 millimeters of lunar regolith to be collected of disturbing the grain structure. Another is the weight, which we aimed for a mass of 5 pounds. The last one would be the stowage of 8 by 8 by 16. So after collecting all of the information that was provided to us, Team Space Cowboys had 5 goals, which consisted of, as I said previously, less than 5 pounds, a stowage of 8 by 8 by 16, be operational in an EVA suit, the device being less than $1,000, and most importantly, like I mentioned, was the collection of the lunar regolith being from 1 to 5 millimeters. Now I'll be passing it on to Abdullah to continue on with the presentation.
Thank you, David. So what you see here is our quality function deployment, or QFD. So we use this to determine our engineering metrics using, as you see on the left-hand side, our customer requirements that were actually given to us by the topic, and using a benchmark, which was the Apollo 16 contact sampling device, which was the sampling device that was used back in the Apollo 16 all the way back in 1974. So this is the device that we came up with. We call it the Ramrod device. As you can see on your left, there is a CAD model of it. This was actually inspired by fence construction equipment, more specifically a fence post digger. So essentially how it would work is the astronaut would grab it by the handle, put it into the lunar surface, give it a little pressure so the lunar regolith can get into the sample cup, and push it outwards, which in turn pushes the clips at the bottom inwards. And I will go over the components more right here. So it's more componentized right here to give you all better understanding of our device. So there will be a top and bottom handle, as you can see at item number 1 and number 3. So this top and bottom handle, essentially how it would work is for volume stowage, they will be able to be compressed using a spring clip. And item number 2, you see our central base. We also have our hinge assembly capturing cup cap, our capturing clips, and the cup base. Now the the central base, the handles will be made out of aluminum, and everything else was 3D printed. So the stowed volume is 3 by 9 by 15.75 inches. The weight is about 4.77 inches, and the total cost for just the equipment was around $260.99. I will now pass it to Michael to get a little into our stress analysis.
Thank you, Abdullah. So in order to verify the structural integrity of our device, we did some stress analysis on our most critical components. For geometrically simplistic components such as the handle assembly and the hinge pin, those were done with hand calculations. So what we would do is we would apply a simulated load on the handle assembly, which would get our reaction forces. One of those reaction forces was on the hinge assembly, and we used that in addition to our safety factor of 2 to determine the diameter of the hinge pin that was used in the design. For more complex geometric shapes, such as the capturing cup base, we did use finite element analysis to determine our safety factor there. And in this case, the capturing cup base has safety factor well over 100. With our structural integrity verified, we were able to start our prototype development. As he said, the hinge components such as the hinges, the clips, the capturing cup base, and cap, those are all 3D printed, which allows us to do some rapid prototyping and get immediate feedback on our design as we print it. Components such as the central base and the handles are supposed to be machined out 6061 T6 aluminum. However, due to some machining delays, we were having to improvise with some of the plastic and print those to bring the device together. We did go through a lot of iterations on our device, and I'll start off with talking about the clips. They originally used to look like the picture in the bottom left, where they are these really bulky clips that not only had secured the sample inside the capturing cup, they also had to hold up the weight of the device. That worked okay, but the blunt surface on the clips didn't allow the device to go well deep into the surface that we needed to capture that 1 to 5 millimeters. And so we ended up with a redesign where it looks something like on the top right. That's our current design, where we took away its requirement to have to hold up the weight of the device. Instead, it is just solely focused on capturing the sample. It allows us to thin them up and can slice through the soil better when it does put it into the capturing motion. Our second component would be the capturing cup base. We started off with something that had no edge on the bottom, and of course we had to make room for those big capes that we had before. And we also had a thread-like design where we would screw onto the capturing cup, which you'll see in the next slide. That was okay and all, but except the capturing cup with the thread design, we couldn't get the bush and tabs to line up right, so we had to switch to a more generalized design of having a notch and groove kind of design, where it would slide in and then rotate about 10 degrees to lock it into place. And then, like I said, the last part was the capturing cup cap. It used to have the threads, and now we have those grooves on the bottom inside that will secure it to the capturing cup base. The clips on the top, they used to be made of the same material as well, of tough PLA. However, when we tested it, if you made them too thin, they would snap off the cap. If you made them too thick, they wouldn't bend at all. So we had to go back and redesign it with using PETG, which then would insert into the capturing cup. As you can see, it has the notches in the middle, in the center image. Once you input those would be able to bend and they could fit into the central base for device put together. So with our device created, we did want to test it on its functionality. So we tested how much it could dig into the soil, and then we also tested how much the grain structure was kept. This was done by purchasing actual lunar regolith simulant that NASA uses for their own tool testing, and we put it into a container, and then we put rollers on the side of the container. We would then make a marking inside the sample where we would use a template such as like a cookie cutter or an apple slicer cutter and create a distinct image into the soil. And then we would cover that area with powdered sugar to make a specific design that has a point that we can reference when we do before and after pictures. The sample was also, when you did the pictures before capturing the sample and pictures taken after, and then we can do the image analysis to determine how much that image has moved since the capturing motion. We will also weigh the device before and after to determine how much volume it has captured as well. This trial was done 2 times, one with a foam stopper at the top and one without. Without the foam stopper, we were able to capture a wide amount of regolith inside the chamber. It kind of ranged, and it kind of depends on how the lunar regolith was laid out in the container, but we were unable to determine the grain structure as it kind of blended it all together without having something at the top supporting it. When we did have the foam stopper, it would stop the regolith and keep it, it would press the regolith into the foam stopper so you could capture some of the grain structure. And then we're also measuring what was left inside the cup. You can also measure it as well with the image analysis, and you see those results on the right side of the second table. Now I'll pass it back to Abdullah to conclude us with our conclusions before we continue.
Thank you, Michael. So through our 2 semesters, we believe that we are confident that the Ramrod was a success in meeting both the team's goals and the customer requirements. Now, if we did have more time, we would like to do more structural testing, as well as sample collecting testing, and do an EPA thermal analysis on the device. So we would like to acknowledge TSGC for this opportunity, as well as our professors and advisors, Dr. Hamidi and Dr. Villa. Thank you everybody for listening.
Questions? I know this was supposed to be purely like a mechanical device, but I was wondering if y'all had any sort of during this process, like electrical additions that you thought would make this interesting, or potentially like some sort of sensor additions, like if you had a like grain structure scanner like within it, like near the foam pad, so then you wouldn't have to worry about preserving that grain structure for later.
Uh, yeah, we thought about it would make it a lot easier if you had some sort of actuating motor at the bottom. It would help with the size requirements, where it make it a lot more simple, like an up and down structure. Um, the issue with the electrical components, with the device being so small and the temperature conditions at the lunar South Pole, it would be really hard to keep those electrical components within their thermal limits without using some sort of heater setup, and that would make the device a lot more expensive and bulkier. So I think it was mechanical. I think for a reason for NASA, but yeah, some electrical components would make it easier to determine grain structure.
Awesome. Thank you. All right, one more question. All right. There we go.
So if y'all had on your results slide for the grain image analysis, the percent differences, can you explain how you use those to justify meeting design goals?
Yeah, so those percent differences, what we did is we calculated the maximum amount of volume our device can take. So there was no surface area specified in the requirements, only a depth it had to go. So we chose like microscope slides as like the template for the surface area, and then we multiplied it by the depth of the 5 millimeters per inches. And so that would be the volume that the device was able to take. The percent difference is the actual volume that was captured during the testing. And some of that was more than the 5 millimeter depth, probably because the foam got compressed, or it was just actually easier to push down that day, I guess. And some of it was below, but they all were above the 1 millimeter regolith threshold mark.
All right, thank you, team.
Hello, everyone. My name is Jacob Boyd. This is Zoe Henry, and we are Team Lunatics. And our project for this semester was to design a nuclear reactor to operate on the surface of the moon. A little bit about the reasoning behind this is the future Artemis missions plan to establish the first lunar habitat near the lunar South Pole. But near the lunar South Pole, there are periods of extended darkness. It can be dark for up to 2 weeks there. So solar panels can be oftentimes unreliable. So we would like to come up with a method that would provide reliable power to these habitats without worrying about whether or not we have access to sunlight. A little bit behind our reactor design. Well, first off, the fundamental concepts of a nuclear reactor is it uses a heavy nuclei, usually in the form of uranium-235 enriched. And whenever the atom splits, it connects with other atoms and it splits, and there on, so on and so forth. It creates a chain reaction generating lots of heat and energy. And we will use that heat to power a Stirling engine to produce electricity for ourselves. Nuclear fission can sometimes be a runaway reaction, so we have to control this reaction through control rods, and we achieve that, and we limit the reaction rate so it doesn't go out of control. Radiation is usually a harmful byproduct of nuclear fission, but luckily for us, it is contained inside beryllium oxide reflectors inside the compact reactor, and that contains all of the radiation preventing any leakage. And our generated heat, like I said, can be transmitted to the Stirling generator through the use of heat pipes, using usually a liquid sodium as the transfer method. I'm gonna pass it on to Zoe, to talk about our reactor history.
Hi, so there hasn't been, too much space reactor history, with America, that is. I mean, we did launch NAP-10A in the past, which is still up there, because there was a failure with the spacecraft, which was considered purely for research purposes. It was designed to generate 500 kilowatts, providing the ability to successfully operate the reactors in orbit. It operated for 43 days, until the component failure caused it to shut down. There is some history with Russian reactors. They have a lot more up in the past, but right now our main competitor is China. So leveraging the existing NASA technology through the CRESI project, which is currently proving for 1 kilowatt of output, a confident progression, kilopower was something that they generated later on after testing it through CRESI, which uses enriched uranium-235 fuel rods and controlled using boron carbide rods. It uses the Stirling engine, as mentioned, which has super high efficient thermal energy conversion compared to other like electrical conversion components. And so the reactors were scaled up to producing 10 kilowatts of electricity.
So some of the requirements for our project were based by NASA. We had to produce at least 40 kilowatts of electrical power, and it had to last for at least 10 years. That's with a 1-year demonstration period, about a 9-year operational period. So in order to maximize our efficiency, which would reduce our overall weight of our system, we did a trace study comparing reactor output versus their specific power and their weight. And we determined, that's how we came across the Stirling engine, and it's the highest efficiency engine for this weight class. And so what we decided to do, it operates at a 10 kilowatt electrical power output. So what we decided to do was choose 4 of these 10 kilowatt CRESI reactors in order to meet our total 40 kilowatt electrical power goal. And this provides a lot of flexibility and responding to various power needs, because not everyone will be in the habitat, not everything will be active or powered all the time. And so there'll be varying levels of power draw, and also gives us a little bit of a safety net. If we had one 40 kilowatt reactor that went down, we'd be out of luck. But since we have 4, we kind of have a layer of redundancy there, saying at least we still have 3 others that are running and operating. A little bit about our comps.
So our reactors are to be located at least 1 kilometer from the lunar outpost. In order to maintain astronaut safety and the integrity of the habitat itself in case of any kind of emergency. They will each be placed in their own individual small craters that are found in the area, which we decided to do in order to prepare them for the future evacuation CONOPS, which we will discuss in just a moment.
So our basic setup process will be whenever we land on the lunar surface, we'll have autonomous rovers carry our reactors out, what Zoe mentioned, the 1 kilometer radius at least, and find suitable craters to place them in. Once they place the reactors, they will return and they will gather our radiator vents, which kind of float up like umbrellas, and they will then carry those out, and those will autonomously deploy, and all of our wiring will be hooked up, and they'll be set up and ready to go. A little bit about our evacuation CONOPS. The reason we put them inside of craters is it provides a little bit of a safety barrier to give the astronauts a little bit more coverage so the regolith would absorb some of the radiation. In case the reactor does have an emergency, the reactor would autonomously shut down and the deployment of their control rods to slow down the reaction as much as possible. We would at least detonate small charges around the crater that would hopefully cover the reactor and the regolith, which would even prevent more radiation from leaking out, and give the crew time to retreat either to the return vehicle and allow them to make a decision whether or not the reactor can be repaired or if they need to fully commit to evacuation and retreat on the surface. Like I said, they'll analyze the situation and make some choices. If it's recoverable, they will try to repair it the best they can. If it's unrecoverable, we will then dig up the reactor once the astronauts have escaped, and then we will take it off the lunar surface and hopefully get it away from our habitat to prevent any further contamination.
So there's a little bit of theory in our site selection regarding environmental hazards on the surface of the moon. So first of all, the location that we choose for this the first lunar outpost is in the Shackleton crater, which is located near the lunar south pole, mainly because it has a high potential for harnessing water as a resource. But down in the South Pole it is much colder there, so we have to take the temperatures into consideration. So temperatures can range all the way down to -200 Kelvin in these permanently shadowed regions, which can impact electronic performance and structural integrity by embrittlement and other things like that. Another consideration is radiation from the regolith itself, which can be charged and interfere with the electronics as well. So the ionizing radiation is capable of shredding the electric circuits. Some prevention methods that we have are to place the reactor on a pedestal in order to protect it from that regolith radiation. And as we mentioned, the crater walls will also help block the regolith and micrometeoroid impacts. Special coating on the reactor and its elements prevent particulate sticking and durable material for micro impacts. Reactors will each also be protected based on their location within the crater, as they will be placed near the crater walls. And yeah, they also are made with very thick material. They have a very robust outer casing, which will protect them from any other environmental damage that can occur on the surface.
So a little bit about our power allocation CONOPS. We will a fully operational lunar habitat. Usually, the minimum power consuming subsystems need to require scalable power, and that's what our modular reactors do. They're a very resilient power structure. They're really reliable, and they can provide continuous, reliable energy. Like we mentioned before, with the solar panels being unable to always have access to the sunlight. For the first lunar outpost plants, estimated power usage for all the elements in maintaining the lunar habitat, including life support systems, autonomous rovers, scientific instrumentation, processing, mining resources, and stuff like that.
So these power allocations are based on NASA's proposed first lunar outpost, and the total estimated power demand that they estimated was during the peak crude activity around 12 kilowatts for the habitat, with 2 during times that the outpost will be uncrewed. The reactor generates continuous energy nevertheless, so some of this will be distributed to RFCs, sorry. And then the rovers that will be used as well for both the people and the autonomous rovers for moving the radiative shields and the reactors around can range up to 6 kilowatts. So combining all of these together with the total power demands leads to their total 40 kilowatt power requirement that they assigned. So in order for efficient transmission from the reactor to the remote habitat to happen, there must be a robust system of interferences and voltage conversions to overcome the distance, mass constraints, and the extreme conditions. The Stirling engines on the reactor first generate low voltage alternating current, which must first be rectified into direct current for high voltage direct current transmission, which is chosen because of its efficiency and suitability over long distances with lightweight insulated aluminum cables. This might seem contrary to popular belief, as alternating current can sometimes be better over long distances, but those kinds of effects change a lot on the lunar surface with the lack of atmosphere. So then the HVDC must be converted back into regulated usable voltages for the power systems and components on the lunar outpost. So this will be using voltage conversion and a power distribution unit. They will then be assigned to all of the different subsystems across the lunar outpost.
And lastly, for our power storage, we're going to use regenerative fuel cells. These combine an electrolyzer, which splits water into hydrogen and oxygen atoms. And then we use a fuel cell that combines the hydrogen and oxygen back into water. And that's what generates electricity. Once again, providing another layer of energy buffer to meet the energy demands of our lunar habitat. I'll give a special thank you to Adam Noakes, our professor at UT, and to Robert Knuckles, our NASA mentor, or TSGC mentor from Axiom Space. And any questions?
So I'd like to hear what each of you think the top challenges are with deploying this type of a concept on the lunar surface based on all the work and research you did.
So the top challenge, of course, with any space component is mass constraints. As you've probably seen, reactors on the surface of the Earth are extremely large. And so in order to create like a compact reactor, this has been a very recent innovation and technology that has had to be created. Another big consideration is just being able to transport the reactors without human intervention, which was part of the challenge. Even though the reactors, the kilopower reactor that we did choose, could actually be safe to be transported, just with protocols and everything right now, this hasn't been done yet. It's a really, high risk to just go ahead and propose to do that with the astronauts that are.
And I guess another challenge to consider is, like was already mentioned, obviously mass constraints are a large issue, but like she said, testing is also, we can't really test these things because we've only ever had SNAP-10A that went into space as far as American interests go. So we don't have enough rigorous testing about how these reactors exactly perform on the lunar surface and whether or not our prevention methods actually do indeed work for the environment, the lunar environment.
Thank you, team.
Thank you.
Good morning.
Excuse me.
My name, my name is Roman Rodriguez. I'm the co-captain of the Space Rats. Then we have our team leader, Denise Barragan, Miguel Barragan, and Colin Hogan. I hope you guys are all doing amazing today. We're excited to present our designs for the NASA Spacesuit User Interface Technologies for Students Challenge, or SUITS for short. Sorry, presentation's buffering.
Apologize.
Yeah, SUITS for short. This challenge directly supports NASA's Artemis missions, which aims to land the first woman and person of color on the moon, while also paving the way for a sustained human presence on the moon and eventually Mars. As part of this effort, engineers are reimagining how spacewalks are conducted. This includes developing displays, improving communications between spacesuits and rovers, and leveraging artificial intelligence and edge computing to push exploration forward. Now, Colin is going to share the goals we have for our suits designs.
Thank you, Roman. So our objective for this mission is to create two interoperable UI interfaces. One for a spacesuit and the other for a pressurized rover. Our objective is to consolidate critical data while stripping away anything unnecessary to make sure that you can focus on your tasks. Our other objective is to create a warning and life support system to make sure that you're fully aware of your safety. In short, we've to turn complexity into clarity and increase both team efficiency and safety. So we'll start with our spacesuit UI. Our spacesuit UI centers on an AR module interface with toggleable panels that allow you to curate exactly what you want to see. For example, life support stats, navigational cues, and scanner data to make sure that only the mission relevant data stays in view. And if your hand's busy, that's not a problem. We'll also be making use of voice controls that allow you to summon or to dismiss any of the menus as you please to make sure that both of your hands are free for work. And finally, we'll be making use of a dynamic pop-up system that allows you to pin or move menus that comes equipped with warning and supplemental data that pop up the instant conditions change. Overall, this means that our UI is clutter-free, keeps you well-informed, safe, and on task. Denise?
Hello, I'm Denise. So I will be going more in depth with our space UI. There are four main displays on the screen, starting with our procedure panel, which is located at the top left, which includes two lists, the ingress and ingress, which is an outline of safety steps for entering and exiting the airlock. The second list is emissions task, a checklist for sample collection, which is color coordinated by white indicating a task not started, yellow in progress, and green completed. This color-coded system was inspired by a game Among Us to help UVAs stay organized. Next, moving on to our map, which is located at the top right, with the top-down view and X and Y coordinates, along with a topographic system of the terrain. The map highlights key points such as sample sites, the airlock, and the rest of the crew. The map will also have 3D drop pins that are rainbow coded by placement order, as well as a breadcrumb trail to help EVs be guided back to the airlock. Moving on to the third display, the suit vitals, located at the bottom left. This ensures life support indicators for astronaut safety. If levels become unstable, a full screen alert and audible alarm will be immediately notified to the EVAs of any danger. And lastly, we have the menu bar, located at the bottom right, integrating navigation tools and scientific data. Users can select points of interest, breadcrumbs, and locations for guided routes. The system will automatically limit travel based on the suit's battery levels to prioritize safety. The second panel implemented in our menu is scientific data, which collects all of our samples. This will always be in connection via a WebSocket with our space rover, which I will now pass over to Miguel.
Hi guys, my name is Miguel Bergman. I'll take the opportunity to introduce you to our pressurized rover UI and design. So the pressurized rover will be operated by using what's called a tablet controller device, aka the TCD, serving as both the control and UI system for any information that will help aid our crewmates when they're doing their lunar surface missions. The TCD features a left joystick on the left, functions on the computer mouse. A TCD features a left joystick for forward and backward movements, and the right joystick for steering. A smaller joystick on the left functions as a computer mouse, enabling cursor selection on the screen. Finally, two buttons, the A and the B button on the right, allow selection in the menu, will allow users to select or go to the menu. Overall, this design is user-friendly for anyone to use. What you see on the slide are different menus that our users can use and access, a lot of our data and information. On the top left image is the track, procedure, and scientific data button. Once selected, the TCD displays a rover navigation, scanning procedures on the left. Next, you see the autonomous resource utilizations, which will give users updates over their space missions, such as warnings of dangers, life support, and battery life in their TCD. On the bottom left of the screen, you see the spacesuits in the center. You see the spacesuit telemetry. What this does is you see the crewmate's camera view and information which correlates to what the spacesuit's UI. Next up, you see the LTV telemetry. The LTV telemetry will show cameras, viewpoints of when you're controlling your rover at a high resolution camera quality. Finally, we'll be introducing you to the 2D map. What the 2D map consists of is consist of shapes, which will help crewmates be able to identify where they are, what are the problems, and what are some great pathways for them to in order to do their missions. It will always update them. It will always let them know, alert them in every case they're ever in danger. So I'll offer it to the conclusion to Roman.
Thank you, Miguel. In conclusion, as first-year engineering students, we're really proud of the designs we came up with and all the research we completed. The space rides were successful in our mission to design an augmented reality spacesuit UI solution, as well as a pressurized rover display and control solution. Whether space crew members are storing data on geological samples, completing their egress and ingress procedures, or navigating from work sites on the lunar surface, our designs seamlessly support the crew. We believe our products will be truly beneficial to NASA's Artemis missions. And I'll pass it back to Denise.
Our team is interested in developing a software using Unreal Engine in the future. This design will help EVAs and EVs complete not only lunar missions, but also maybe even Mars. That's the beauty of software. It can be implemented in whatever device is needed. And thank you.
Hello, this is Neil from NASA, the VR Lab. I have a question on your plans for the future AI enhancement. What do you plan to do with AI?
With AI, what we really wanted to do with AI was help the EVAs when being on the mission to be able to scan the samples and implement an AI that will help have information on the samples.
More on that AI section, with these designs, we wanted to focus on reducing the cognitive load on these space crew members. So any light sort of functions we can utilize AI for, like navigating or any sort of communications or alerts, like we mentioned earlier, just have those cues. It'll definitely help lessen the load on the space crew. Any more questions?
Yes. So on your development user interface, did you consider the display technology that you might be using and the environment, the visual environment the crew would be working in, which would drive the colors and font size to increase visibility of the display?
Yes, ma'am. So, in regards to, for instance, the pressurized rover tablet, we definitely wanted to make sure that we were able to control the brightness, for instance, as you guys all know, different parts of the lunar surface, the light varies. And also, for that, we'll be utilizing an LCD display, very similar to the tablets that they're currently using, testing for pressurized rovers. And I'll pass it over to Colin to go over the UI for the spacesuit.
So, in regards to the font size and the color for the spacesuit UI, what we currently have is a placeholder because the lunar surface is obviously a combination of a gray and obviously the black sky, pretty much, as far as I'm aware. So I think the white font that we have, I think, is appropriate. And
One more thing for the spacesuit UI is as we have menus up on the screen and it is augmented reality, we want to make sure that the menus are the opacity on them are you can change them. So you want to be able to kind of see through them so the space crew can be aware of their surroundings. So that's another way of the formatting of the UI design that we want to incorporate into the design. Thank you for those questions.
I have a two-part question. So the spacesuits, since you have the spacesuit vitals, do you plan on, like, for future directions, kind of implementing like the actual astronauts vitals and digitizing, like, okay, this is like their heart rate, etc. And then as far as research, what type of research did y'all conduct and kind of test?
I'm sorry, what was that second part? What part of research?
Because you talked about how y'all developed research and such. How did y'all go about that?
Yeah, so to answer your first question, I'm sorry, could you repeat your first part of your question? I just blanked out.
So you have the spacesuit vitals, but what about for future direction? Would y'all think about implementing actual astronauts vitals?
Got you. So yeah, to answer that question, we would be implementing the astronauts vitals, the whole crew's vitals. And the cool thing about our two interfaces is they'll actually be interoperable. So we'll be sharing the vitals between the tablet controller device as well as the spacesuit UI. And that'll include the biometrics, like you said, the heart rate, temperatures inside the suit, also temperatures of the environment. And then yes, so the way we conduct our research, actually, the gentleman who asked us our first question is our mentor, NASA mentor. So he was able to give us some on-hand experience and tips as well, because he also did suits challenge a couple of years ago. So that was really great help. We also had help from our professor, Kazi Rochette. He definitely helped us do research on spacesuits in general for creating our augmented reality. And since there already is a lot of research being done for augmented reality and taking it to the lunar surface, we just looked at those models that NASA is using, and that goes just the same for the tablet controller device.
All right, thank you, team.
Thank you all.
Hello, good morning. We are effectively grounded from Texas State University. We were tasked with designing the motherboard for a radiation-tolerant laptop based on the high-performance space computer from Microchip. This processor is currently in development, so we selected the Microchip Polar Fire as a suitable replacement. Over the next several minutes, you'll hear more about our work for this project over the last 2 semesters, but I'm going to start with a little background. NASA is committed to going back to the moon and beyond. They will need a radiation-tolerant laptop to facilitate this. On Earth and low Earth orbit, digital electronics are largely shielded by Earth's gravitational field, but in space, cosmic radiation poses a serious risk to digital electronics. This can cause single event effects, which are bit flips in memory or registers. They can also cause latch-ups, which is an inadvertent short circuit in MOSFET. And it can cause a total ionizing dose, which is where the cumulative effects of radiation damage components over time. These effects can cause data corruption, faulty logic, system crashes, or even total system failure. And now Aidan will tell you more about the HPSC processor and the Polar Fire.
So that's where the HPSC processor or high performance space computing processor comes in. NASA is currently in collaboration with Microchip developing a radiation hardened processor for space applications. It's going to be based on the RISC-V architecture, and unlike other common architectures like x86 or ARM, RISC-V is open source, making it very cost effective. Currently, this processor is expected to provide significantly higher performance compared to existing space-grade processors. However, this processor is currently still in development, so we needed to find a suitable alternative to develop our board around.
we decided to go with the PolarFire as system on chip after conducting a trade study, as it's also manufactured by Microchip and uses the same RISC-V architecture. There are several development boards available to use with this processor, and we opted to go to use the Icicle kit as it had the best peripheral capabilities and allowed us to build on top of our design.
Our team used the Icicle Kit development board as a starting point for our custom board design. Having PolarFire SoC as the main processor, we were able to prototype with it and confirm the feasibility of using this processor for our needs. During the development of the schematic and the layout, we were using the schematic and the layout of the Icicle Kit development board, but also we made significant changes to the design to better align our board with the project's goals, which is creating a RISC-V processor-based main board for a laptop. During the development, we identified the parts that went obsolete and are no longer manufactured, so we had to replace those or remove them completely. We also got rid of unnecessary features, as well as added those that are essential for our end product. This project is meant to be iterative, so future teams will build upon our design and add new features, remove things that are no longer needed, and eventually, when HPSC is around and it's released, they're gonna swap it out with PolarFire and therefore create a radiation-tolerant crew laptop. From there, to bring our design to life, we had to start with the first major step, which is creating the schematic.
And so we were able to obtain the schematics of the Icicle kit from Microchip, and from that we were able to use them as a reference design to create our own board using All Team Designer, which is the same software that NASA uses to design their hardware. So behind me, we can see the schematic pages of our board. So each page represents a different system within the board, and how these systems, such as the memory chips, the processor, or the graphics systems, are interconnected. So these schematic pages serve as sort of a blueprint that we need to begin the physical design and layout phase of our project, where we're actually placing components on the PCB itself.
So as Josh mentioned, the schematic, it acts as a blueprint, but we still need to lay out the physical components of the board itself. So how we do this is we do what's called PCB layout. As you can see on the photo on the screen, that is a 10-layer board, and each color consists of a different layer on the board. You can think each layer has a whole bunch of different circuitry and traces routed on it, and you can use what's called vias to connect those layers together. This allows you to have a compact but also very complex board that doesn't take up a whole lot of space. Kind of zooming in on that board in the middle, discussing the PolarFire system on the chip, which is the main processing unit of our chip. One of the major things we've had to do is fan out these processors since they're so compact. How we do this is, since we have a 10-layer board, we can fan it out by sending those vias down to different layers and then routing out on a specific layer itself. So then you can have that compactness kind of separated out.
As my team mentioned, this is an iterative design. We've been working on this for the past 2 semesters, and we're excited to hand this off to the RadCAD Sentinels. From there, they will look at our design, validate, continue to improve, and hopefully after the HPSC is released and enough teams have worked on it, we will have a radiation-hardened laptop mainboard. We'd like to thank Mr. Justin Batista, our NASA sponsor, Mr. Jeff Stevens, and Mr. Mark Welker, our faculty advisors, for helping on this project. Any questions?
Did you have any trouble doing the layout for the 10-layer board, or was it your first time?
Yeah, it was our first time. That was probably one of the most challenging aspects is usually introduction to PCB design is with usually maybe even a two-layer board. You're just working the front and back. So it definitely was interesting going up to 10 layers because then you have to worry about dielectrics in between and yeah, a whole lot of other physical properties that go into board design. So yes.
So if I understand correctly, you're working on a true laptop design, and what I didn't see in your presentation is the features that you were looking at for a true laptop. Are you considering all the features that are ordinarily in a laptop? And if so, how is that allocated among the components?
Right. So the features we're adding to the development board are the USB connectivity as well as audio. And essentially, yes, the laptop is supposed to be as powerful as regular commercial laptops because that's what they use at ISS at the moment. Uh, the main problem is going into deep space missions, radiation can hit the electronics and destroy the laptop. And also, as I remember, if I remember correctly, the crew will also use the laptop to control various vehicles on the moon and on Mars. So we essentially designing the laptop that will be just like a commercial laptop, but will also have the capability of withstanding the radiation.
Other questions?
There we go. So how did you all address component selection during your design phase? Were you looking at, radiation tolerant components or using a database? How are y'all thinking about that?
So, as we understand, NASA has a database that lists off components that are inherently rad tolerant. On our first selection of the board, the one that we're designing, we haven't looked into that database, but a future team will look into that once we grab the HPSC, but that hopefully comes out in 2026.
And I would like to add, on top of that, we used the bill of materials of the ASCII kit to roughly understand which materials we need. And then we also researched our own subsystems and new features that we added to understand which chips and the components we need.
All right, thank you very much, team. We will have a very short 5-minute break and reconvene at 9 o'clock. The next 4 teams, if you could get your presentations ready. All right, everyone could take your seats again, please. All right, good morning. Thank you for joining us again. Our next group of presentations is starting off with the cosmic javelinas.
Yes.
Good morning, everyone. We are the Cosmic Javelinas from Texas A&M Kingsville. I am Marco Hernandez. This is Kevin Araiza, Ryan Avila, Mark De Hoyos, Angelina Moreno, and Emilio Villarreal.
So some background, we are doing the Human Exploration Rover Challenge. We will be specifically competing in the HPV division, which tasks teams to design and build a human-powered rover to overcome rough terrains that occur during the course. Just a disclaimer, this is not meant for actual lunar terrain.
In the HERT competition, there's a total of 10 obstacles. There's not necessarily any designated categories or groups for them, but our group decided to group them up for convenience sake and to help out with our design process. Obstacles, or the first group consists of obstacles 1, 2, and 6, which are all based around bumpy terrain with alternating terrain elevation. The second group of obstacles would be 3, 4, and 5, which are all based around ascending and descending terrain. This is essentially the ramp section of the course. The third group consists of only one obstacle, which is obstacle 7, and it's because it's the only one that's heavily reliant on the actual steering capability of your rover. With the fourth group being 6, 8, 9, and 10, in which they all consist of traversing through a pit of either gravel or pebble-like terrain, mostly meant to test the traction of your wheels.
For our competition objectives, the main goal is to complete the 1.5-mile course in under 8 minutes. Some further obstacles or competition objectives are our weight has to be underneath 130 pounds, our turning radius has to be under 10 feet, and our braking system has to hold our drivers at a 30-degree incline, and we need to have a 12-inch ground clearance between the bottom of our driver's seat and ground. And finally, our maximum dimensions need to be 5 feet in length, width, and height.
Our rover features reverse gears for its normal bound direction, angle seats for safety, four-wheel drive for power, indirect steering, double wishbone suspension, bucket seats for comfort, and hinge for easy transportation.
We chose indirect steering due to its mechanical advantage. And indirect steering has 2 tie rods which connect to a pivot point, which is located underneath the handlebars.
With Ackerman steering, we have our tie rods being shorter on one length, so that way it's sharper, causing tire alignment with our front and wheel wheels. It also compensates for slippage. Our steering angle calculations with Ackerman geometry being considered. We have our wheel-to-wheel length, which is represented by T, which is 40 inches. The length between our axle, rear and front, is 45 inches, and our chosen turning radius of 120 inches, which is a constraint in the competition, which is you have to have at max a turning radius of 10 feet. And our difference in steering angles between the inner and outer tires is 6.45 degrees, which is by no means perfect Ackerman geometry for our wheelbase, but it was the best that we could come up with our chosen steering mechanism. Yeah.
For suspension, we chose a double wishbone. It was the best and most efficient option due to all the obstacles having different types of terrain.
Some of the safety features that we implemented are low center of gravity, which prevent the rover from
turning over on like steep hills, reclined seatings to decrease the risk of backstrain, the bucket seat designed for secureness and support for our drivers, and no rough or sharp edges. Here's our seat design. Some of the key features that we did is the bucket seat, like I said previously, for support and secureness, holes to reduce the weight and strengthen the structural integrity. Back-to-back arrangement for the low center of gravity and interchangeable rear seat, which you'll see in a couple slides, be able to exchange with the collapsible crate. Those are our full-scale dimensions and then the half-scale dimensions.
To fold the rover in half, we designed a hinge in order to be below the competition limits. The hinge will be welded in the middle of our I-frame, and the dimensions shown are for the half scale that we brought. For our locking mechanism, it was designed with the intent to hold the unfolded and folded positions on the rover. It is similar to a ball and socket joint, and the dimension listed below are for the half scales again.
Like Ryan had mentioned, the collapsible crate can be interchanged with the rear seat of our rover. It can fold from 4.2 inches to 0.6 inches. It's light, easy to transport. It is mainly used to collect our samples, specimen, and cargo.
This is our final CAD design, implementing the previous slides with bucket seats, steering, pedals, the three spiral wheel designs, control arms, and the axles.
For our 1/2 scale, our components include an I-frame design made of steel, our arms made of copper, and aluminum rods. We also have 4 non-pneumatic wheels, rover axles, ball and socket joints, weld covers, locking mechanisms, and shocks.
So for the making of the half scale model, we started with getting the dimensions of the full scale and then reducing them to the half scale. And in the pictures, you can see the layouts of when we cut the pieces to see that it is roughly as close as possible to the full scale dimensions if it were to be multiplied. So as we made these out of steel, we of course need to weld them. We don't know how to weld, so we learned as we went. Then the machinist showed me once, and then he said, "You can do it." And then we couldn't weld on the weekends, therefore we went to Harbor Freight and we bought our own welder. So for $180, YouTube can become a local welder.
For painting the rover, we sanded it first, removed the seats so we could paint the frame and the seats separately as they both had different colors.
Here's our colorful bill of materials. The most expensive things were definitely the welding equipment and the steel and copper tubes. Our total was $694. It's crazy.
Not everything was out of pocket. We used the resources that we had around campus. That's just estimated. In conclusion, we were able to successfully build our rover. We're back here in the corner if you want to come check it out. The hardest, most difficult part was definitely the welding, learning how to weld. It's pretty hard. Future plans, we hope to coordinate with student organizations such as the Society of Automotive Engineers or the American Society of Mechanical Engineers, and hopefully our university can participate in the competition. Here are some of our references, acknowledgements, Dr. Tim Irvin and Nina for coordinating everything, communicating, our advisors, Dr. Larry Peel, George Salazar, and Mr. Grady, Dr. Aginiga, our machinists, CJ and Rod, also Caesar, and some colleagues that allowed us to borrow their 3D printers for 3D printed components. Are there any questions?
So your diagram showed the tie rods directly connected to the steering shaft, right?
This one?
Yes. So my question was, how would that translate the rotational motion of the steering shaft to linear motion of wheels?
So on our half scale, we have a bearing that's located underneath the seat, which has the steering. So for us, we're using uh, underseat steering. So it has like two rods that come up like that, and you move it like that. It's not necessarily steering wheel, which is connected to like a plate, which we call like the pivot point. And then that's what's connected to the tie rods, which are connected to the axles, and that's able to steer it. Yep.
Did y'all try to do any testing of sorts for kind of like tip rates? So say like one wheel comes, airborne, how do y'all go about that and stabilizing your mechanism for space? Because there's obviously curves, etc. So with that uneven space, how are you going to be able to stabilize it to where the astronauts don't tip over or anything like that, and it doesn't become damaged?
So like one of our safety features is the low center of gravity, which will prevent from tipping over. And then we also have coilovers on our half scale over there, which will also like absorb suspension and stuff like that. Partially. Any other questions?
One more up front. Okay.
I know you said it's not designed for the moon, but if you would want to use it on the moon, what improvements would you make?
Some improvements we would make would be sealed bearings and just overall dust mitigation and the increasing size of the seats to accommodate for spacesuits and the overall lengthening of the entire rover to, of course, for spacesuits again to limit joint movement since they're already limited as is with the spacesuits, and of course to increase the pedal rod size and the sizes just in general for the overall size of the suits.
Thank you, team.
Hello, we're Team Hephaestus from Texas A&M, and we did a lunar surface nuclear reactor conceptual design and concept of operations. I'm Alex Webb.
I'm Caleb Malone.
I'm Summer Barnesville.
Connor Wiley. Isaac Nikolаев. And I'm Sid Reddy.
So we have a problem. We need power on the moon because we can't get anything done without that. If we want to have lunar inhabitants or anything of the sort, we can't do that without power. So we have multiple requirements to get something like that on the moon. We have to get the conceptual designs, the layout. Why do we even need it? We have to distribute the power once we have it there. Concept operations once it's on the moon, how do we get off if anything goes wrong, and where do we even put it? You might be asking, why are we even doing nuclear power? Because why can't we just use solar panels or something else we use on Earth? Well, solar power is not very reliable. With 14-day nights, we can't get power day around, so that's not very viable. Wind power is, there's no wind. Hydrogen fuel, while it's reliable, it doesn't provide enough power that we need to do something on the moon. So that also doesn't work. So nuclear power is our only option.
Okay, so we narrowed it down to three different reactors. We narrowed it down to three different reactors. So we had the SP100 reactor, the Krusty reactor, and the Rolls-Royce microreactor. Two of these reactors had slight issues with them though. The SP100 is very big and lacks capabilities for modularity. The Krusty reactor operates on the order of kilowatts. That's not enough for a lunar base. However, the Rolls-Royce microreactor is both modular and able to operate on the order of megawatts. So let's take a look at a brief overview of our reactor design. We have a fuel compartment which will contain triso fuel pellets, and we have a radiator tube which will contain steam, and that steam will be radiated off so we don't have to continually get water from an external source. If you look at the triso fuel design, we have an internal fuel kernel consisting of uranium oxide, and there's two layers of both silicon carbide and pyrolytic carbon to prevent fuel meltdown in case of an emergency.
So now we have to figure out how we're going to get it to the moon. It follows a pretty basic procedure. So we decided to go with the SpaceX Starship because it's a very modular design. It has a lot of space. We would ideally transfer multiple reactors at a time. Again, it's very modular, so that's ideal. We want to securely contain the rocket in case there's some sort of disaster. We don't want nuclear materials raining down over Florida or something. So we securely contain it so it's not damaged due to shocks during the transfer. There's also extensive legal approvals we have to go through, many departments for launching a nuclear device into space. Governments generally don't like that. So it would have to be a very extensive plan to cover all of that. So once we launch it, it'd be a pretty standard procedure: transfer orbit to the moon, circularization, descent down, and we picked the lunar south pole for a location. We'll get into why that. But the reactor would be needed to be continuously monitored to ensure that it's not damaged during the transfer, because damage could lead to contamination, many bad things. So this is a very special payload that would have to be monitored differently than just a normal payload. So once we land, we'll have two parts. We'll have a crane system with a pulley and a very simple dolly system. This will make it easy to transport. The reactors are very heavy, even under moon gravity. So this will just make it very easy for the astronauts to move them around with limited mobility. The installation ideally is very simple. You're not going to need very complex tools because they won't have access to it. So it should be very smooth, very ideal, and very human.
So as we mentioned earlier, we did choose Lunar South Pole as the location for this reactor. And the main reason behind this is because of its perfectly shallow regions holding significant amount of water ice. Our research specifically stated 1.3 trillion pounds. And the reactor will be strategically placed on the edge of the Earth rather than inside. And this for two main reasons. One, we don't want any of the water ice to get contaminated in the event of radiation leak. And two, we want to make sure that the reactor is easily accessible for maintenance procedures. And in order to make sure that we can establish communication with the reactor, LunarNet infrastructure will be used, but will need to be constantly maintained.
So this is our power distribution model. In the middle, that's our Rolls-Royce microreactor. And here we have it surrounded by a dome to allow for it to generate electricity through water power. On the side of that, the left, the box is where we could charge a lunar terrain vehicle. On the right side, we have our flywheel storage. which is what we chose as our primary backup energy system, which we'll get more into in the next slide. And then in the top left, we have our transformers, which is part of the safety protocol we included to help step up and level down the high voltage current. And then here we have a decision matrix of our backup energy storage selection. So what we have here is just kind of showing that the flywheel storage was the obvious choice because it is better than fuel cells, lunar regulation batteries, and supercapacitors in important categories like cycle life, temperature sensitivity, energy density, and power density.
Now that we have our daily life of how we're going to map out the power, we needed to take into account all the risks. And we compiled a risk of, this is 15 out of our 100 different risk matrix that we had of an order of risk score. And that is just a combination of likelihood and impact. And the higher the risk score, the more we wanted to focus on that, with a few examples of meteor debris, the energy wire getting damaged, and lunar dust infiltration. This is just a visualization of just some of the different things we have. And the red colors we have are the ones we really wanted to focus on and implement within our designs. And we have a lot of redundancies within our designs of covering all the different mitigation strategies that we use with all of our risks.
So a quick summary of our presentation. The Rolls-Royce microreactor is the best reactor currently used for this mission. And the fuel that will be used for this reactor is TRISO fuel. In order to transport this reactor to the South Pole or the Moon, we'll be using the SpaceX Starship. And the LunarNet will be used to establish communication, but there will need to be maintenance. And then in order to make sure that we can power the lunar colony, there needs to be a proper power distribution system and transmission system. And finally, we have to make sure that there's proper risk mitigation and evacuation protocols required in order to ensure human safety. And some of the future operations that we've thought of are once we can bring more lunar reactors to the Moon, we're going to create more lunar colonies. And the power is also going to be used for mining operations to extract rare earth metals. And eventually we want to make the Moon a refueling station and launch point for future missions to places like Mars and maybe even further exoplanets. And finally, we want to completely colonize the Moon at some point to make humanity a multiplanetary species. And then we'd like to thank TSGC for the opportunity. And then we'd also like to thank Mr. Robert Knuckles, our mentor, for his continued guidance and support of the development of this project. And finally, Texas A&M Think Tank and Aiden Campworth for giving us the opportunity to be here. Thank you so much.
Any questions?
Based on the TRISO isotope or uranium, whatever the design is, how many years would the nuclear reactor power? Is it hundreds of years, millions of years?
Okay, so our rough estimate is about 20 years, which gives enough time for continuous operations to go up to the Moon to refuel the reactor. 20 years is plenty of time, given that the objective that NASA gave is 10 years. So in terms of fuel, we have no problem regenerating it.
Morning, I'm Robert Knuckles, Vaxian. My question to ask you is, looking at the design of this, what do you think the budget do you think NASA has to set aside to design and launch this successfully?
Oh, of course, yeah, we actually got an appendix for that. So a reactor module currently is hundreds of millions to research and develop, but once developed by Rolls-Royce, we're estimating it'll be about $10 million per unit. Transport is going to be the most expensive factor, at roughly $100 million, given the estimates that SpaceX gives for lunar transport in the future. Flywheel storage, going to be about $2 million for that technology. All the auxiliary power architecture, so we're talking batteries, transformers. That's not good. Oh yeah, all the auxiliary power architectures, so we're talking also the dome, transformers, etc. It's gonna be about 20 million, and our deployment systems will be 1 million. That being said, we're working with NASA here, so expect everything to be 5 times more expensive than Let's actually go back in here a second.
One of the concerns with nuclear power is obviously waste storage. Was that something you considered? And if so, how did you deal with this issue?
Oh, yeah, of course. So, in terms of waste, because waste generation is actually a very long-term process, we expect our, decade, like on a decade basis, we'll have operations going up to the moon and down. And during those operations, waste will be transported safely back to the Earth. Due to the structure of our TRISO fuel pellets, is actually our waste is very safe, and it can be disposed of as nuclear waste like any other thing on Earth.
You chose the south pole of the moon because of the water ice that you needed for the reactor. So where will the colonies be that you're going to be powering? You're going to have transmission lines extending miles across the moon. How's that?
Yeah, so the idea is that, yeah, we will be having transmission lines that do actually extend across the moon. The colony itself will be placed the safest away from the specific reactor, and through the use of transmission lines, we'll be supplying power, and through the use of pipes, the water will be extracted and sent to the colonies.
All right, thank you, team.
Hi everyone, we're 13 characters and today we'll be talking about our lunar rescue concept for incapacitated EVA crew. So first, before we begin, let's go over some abbreviations and some vocabulary that will make our process a little bit quicker. EVA stands for extravehicular activity. Extravehicular activity would be any activity that is outside of the lunar spacecraft. IC and HC do stand for incapacitated crew and healthy crew. ICR stands for incapacitated crew rescue craft. Well, without the craft, but it does talk about our cargo. This is the table of contents. Today we'll be going over our team introduction, purpose of design challenge, design parameters, rescue profile, and then at the end we'll have a Q&A to answer any questions. Let's introduce our team. Let's introduce our band of characters. All right. We have our team leader, Jonah Davies. I'm Natalia Gomez, and I'm the team co-lead. And then we have our three other members. We have Giovanni Trujillo, Ronald Fioa, and Jason Tom. One of the goals given to us for this challenge was to create an ergonomic and compact ICR that is able to transport an incapacitated member to the lander in under 2 kilometers. Some of the key requirements was that the cart would have to withstand harsh conditions, such as but not limited to extreme temperatures, abrasions and regolith, and have the ability to traverse steep inclines up to 20 degrees, as well as being quick and easy to use.
Hello. The cart features 6 major components, which are highlighted here for identification purposes. The first major component is the seat, which features a cavity for the incapacitated crew members' life pack. The seat is at 60 degrees, which is optimal for an incapacitated crew member. And the seat will have dual retractor seat belts in order to strap the crew member to the cart so they don't fall off. Behind the seat is the winch, which is in an enclosure to protect it from regolith and lunar debris. The winch will be powered by one of the 4 motors on the ICR, and the winch will connect to the incapacitated crew members' clips on their waist. And lastly, we have the ramp, which is going to be inside the cart. The ramp features 2 stakes at the end, which can be driven into the lunar surface in order to keep the ramp stable, as well as the ICR stable, as the incapacitated crew member is being placed onto the cart.
Right, so here we got the frame and battery design. The top, will be our frame design. It is the dimensions are 62 by 18 by 6 inches. It's constructed out of an aluminum 2219 alloy. It has a welded tube truss structure with an outer sheet and sorry about that. The tube and truss structure with outer sheet is good because it makes it strong, but it also makes it light for lunar operations. The bottom part in pink are the batteries. It's 4 batteries. Each battery operates on its own. So in case one battery goes out, the 3 are still working. So nothing wrong could go there. Each battery gives an output of around 775 watt hours of energy. So for a combined total of 3,100 hours. It's very modular. So in case anything needs to be replaced, that could be easily done. The outer sheet for the batteries is there to protect it from lunar dust or regolith because in the moon, well, that could be very dangerous for us.
The storage. The storage is 4 different compartments, 2 larger ones. The dimensions will be 12 by 12 by 6. And then the 2 smaller ones will be 12 by 6 by 6. There will be one of each on the back of the, located on the back of the ICR, and they can be easily opened like a cabinet. And then also from the top, it can be opened like a chest. This is convenient for storage and for the stored items. And then we're also implementing a system where it can be easily detached from the ICR in case somebody's incapacitated, so there's less weight for the transportation back to base. And on the harness, it will be mounted on the front of the ICR. It's going to be the main way that the ICR will be moved, will be transported. It's going to be 2 separate aluminum 2219 alloys, and then there will be a distance of two and a half from each other. They're going to be 36 inches long. They're going to be at a 34-degree incline, so they'll be 3 feet and 3 inches above the ground. They will provide control of the ICR through a brake system, and on the brakes, it'll be completely mechanical, which with no hydraulics included because due to the temperature on the moon, it would not be able to withstand that. It would utilize a tension-based system to apply the brakes. So basically, kind of like how a bike uses, the more pressure is added, the harder it will be, the harder the pressure will be on the ICR. And then we decided to use a Vectron or steel wire to connect the brakes to the harness lever. And then finally, we decided on metallic brake pads for better performance, as it will have better tension and better friction on the moon surface.
The ICR will have 4 separate motors, each with 1/6 horsepower. Only 2 of these need to be active at a time for operation. However, all 4 can be used in the event that you are on steeper terrain and need more power. You not move. Oh, am I going the wrong way? They are modular, so in the event that one of them does fail, they can be replaced, they can be swapped. So there is redundancy. Like I said, only 2 need to be active, so, if 2 of them do fail, you can still use the cart.
We decided to go with a double wishbone suspension for the ICR because of its great performance across the board. It is heavier than some other options. However, any suspension with a similar level of performance is significantly heavier and more complicated. Double wishbone is still relatively complicated. However, despite that, its benefits outweigh that downside. The wheels we will be using for the ICR will have an 8-inch tread and an 18-inch diameter. The tread will consist of a grid lattice with W-shaped extrusions to basically dig into the lunar surface as it's moved and gain traction. And we decided to go with a lattice for the majority of the structure to allow for passage of lunar regolith through it and prevent clogging and build up, which would impede its performance. In the event that one of the crew does become incapacitated, these are the series of steps we would follow in order to retrieve them and return to the lander. So if that does happen, the healthy crew member would reorient the ICR so its rear is facing the incapacitated crew member, and then they would take the ramp out from the ICR and drive its stakes into the lunar regolith to stabilize it and ensure it's about 2 or 3 feet away from the incapacitated member. Once that has been done, they will pull cable from the winch and hook it up to their waist clips on the Axiom spacesuit on the incapacitated crew member, and then pull an extra 2 or 3 feet of slack so that they do not get jolted when the winch is activated. Once that is done, they can activate the winch and guide the crew member up the ICR, making sure they don't go up sideways, fall off, get stuck on anything, and prevent general mishaps. Once the incapacitated crew member is situated on the ICR, they will have to be manually reoriented so that their life pack is resting within the cavity on the seat and they are flush against it for stability. And once that is done, the healthy crew member can take the dual retractor seat belts, they can fasten them, tighten them, make sure the incapacitated crew member is stable, and then they can unhook the winch, wind it up, go back, take the stakes out, put the ramp up, hook themselves into the harness, and then they can return to the lander and assess the situation. Questions?
Realistically, in an emergency situation where they have to get the ICR back to the craft as quickly as possible, I assume these other parts that have coming off, like the ramp, they can just leave it there if they have to.
If they needed to, and the motors weren't working, and there was a sufficient level of weight, the ramp can be just left there. The storage compartments can just be dropped there. I think those are the only detachable components we have right now, but that would reduce the weight a decent amount. I would probably say 10 to 15 kilograms.
Did your concept consider, is it assuming that the system is pre-assembled on Earth and kind of delivered on the lunar surface, or is it more we need to assemble it when it's needed? And if it's the latter, maybe a few thoughts on what that would entail, the amount of time, or how easy this would be to snap together, consider a crew member wearing a spacesuit and all of that.
We intend to have it assembled here. It would be ideal if it does need to be assembled on the lunar surface, though. We would incorporate a series of bolts or, something like that, maybe clips that are simple and easy to do. You don't need a lot of mobility to get them in. They're big. It would be relatively simple to do it in the spacesuit because of the amount of space you would have.
Speaking of mass, what do you predict the mass of this ICR concept?
At a guess, I would say probably between 80 and 100 kilos.
Okay. And then for your nominal traverse, how is the crew transporting this?
They would be strapping themselves into the harness and bringing it with them. It basically acts as a driver's seat, so to speak. It would hook onto their waist clips, and then you would have the lever for brake control, and there would also be L rods, which connect to the forward drivetrain, allowing for steering. There will be pressure sensors in there, so as they move forward, the motors will activate and assist them in movement.
Perhaps my question wasn't clear. So that's what happens during an emergency, that when they're just normally traversing on the moon, where is this design? Is it traveling pushing it along, or where is it operating?
It's the same set of movement for emergency or non-emergency. It uses the same concept. They wouldn't be doing anything different. It's in our opinion, safer and easier to be pulling than pushing it.
Any other questions? All right, thank you, team.
We are Team Nova, and we are composed of myself, Mario Adames. On my right is Diego Zuniga. Behind me is Oscar Franco, and the man with the silver blazer, that's Eli Fuentes. We were tasked with building a design and development of a lunar rover with extreme navigation or through extreme terrain, and it being capable of building a berm. Now I'll give everybody a few seconds to familiarize yourselves with our presentation outline. And in the meantime, I'll give you some introductory information on why we're doing this. So the point is to make this design within the criteria and constraints of the Lunavotics 2025 Challenge, which is a competition in which that NASA holds, which they invite teams from different universities to make a design with a specific task or purpose, and then all the teams go ahead and compete with those similar designs. And the specific purpose or objective of this year's competition was to build a berm. And for anybody confused on what a berm is, it's pretty much just a hill. So if you push a bunch of dirt onto one spot, you build a berm. And the reason why NASA is interested in this is not so much the berm itself, but it's the leveling that happens because of it. Because anytime you want to build something, whether it's to put a nuclear reactor or habitats or wherever it may be, you kind of need that flat space. I mean, even here on Earth, right, when we build houses or buildings, the leveling is the first thing that happens. And now I'm going to hand off the presentation to Oscar Franco to speak about the project goal summary.
So as a brief summary for our project goals, we were tasked to create a lunar rover that can create flat surfaces for future NASA missions. We were given constraints by NASA, such as a volumetric dimension constraint of 1,500 millimeters by 750 millimeters by 750 millimeters. Additionally, we were given a mass constraint of our lunar rover must be under 80 kilograms. And lastly, we were given a constraint that our lunar rover must be able to push at least half a kilogram of lunar regolith. So on the next slide, we'll be talking about our final design. We began prototyping based off our CAD model, which meets the volumetric dimension constraints given by NASA, with our final dimensions being 203 millimeters by 177 millimeters by 343 millimeters. We began prototyping by purchasing a tank chassis that has two DC motors. Afterwards, we designed a frame plate that had two purposes. One, to be able to hold all our electronic components, and second, to be used as a counterweight. We predicted that since we were doing a bulldozer operation to be able to push the regolith, we predicted that the nose of our lunar rover would want to push into the sand or into the regolith. So we decided to use a frame plate to use this weight distribution to push weight to the back. Additionally, we assembled our frame plate to our tank chassis, and we designed our bulldozer blade, which was the most complex part of our project. We designed it in such a way that it has a chamfer at the tip of it to be able to create that flat surface we're looking for. And we also gave it a big radius because our main function of the bulldozer blade was to push regolith rather than pick it up. And now Elias Fuentes will be guiding us through our electrical components.
All right, thank you, Oscar. So for key components for our electronics,
is composed of three things, which is the Arduino microcontroller, the motor driver, and the 12-volt battery. The Arduino controls most signals and logic operations. It's what basically controls our robot. The motor driver is what controls the motors. Obviously, it dissipates the power from the Arduino itself. That way, the Arduino doesn't be overcharged by the battery. And the 12-volt battery is what powers the entire thing. The power distribution, as far as the battery, it's connected to both the Arduino and the motor driver, as you can see on the right. That is our schematic. So our schematic, it's composed of the motor driver, the Arduino, and the battery. And so what it does is the motors are connected to the motor driver, and the motor driver has four different signals or four different outputs. Those two outputs, one is for one battery, the other one's for the other battery, but both have two specific outputs, and one of them is for the power or the speed, the other one is for direction. And it is also connected to the Arduino, and what that sends is two different channels. That way, it sends it directly to the robot and kind of commands or sends the code that is implemented in the Arduino. I did confirm that the Arduino carries C++, so that is the code that we use for our robot itself. So the system is designed for simplicity, reliability, and low energy loss. Next, we'll talk about prototype testing. We'll have three different types of prototypes, testing, and it's for mobility, terrain testing, and blade performance test. And then our final is our electronics validation test. So as far as our mobility and terrain testing, our plan is to drive the rover over sand, gravel and mild inclines. Obviously, our expected result is for it to drive smoothly without any mishaps or, kind of playing the field. Secondly, for our blade performance test, our goal is for that to push some regolith, or specifically 1.44 kilograms of regolith, and to burn, as we mentioned before. And then finally, our electronics validation test, making sure that everything's powered perfectly, everything's powered fine. I think some of you guys noticed that our motor driver burned out yesterday, so we probably have to switch that out, but that's part of our testing. So we're definitely going to take that into consideration and move forward with our prototyping testing. All right, next I'll hand it off to Diego to speak about technical content. Thank you. Thank you, Eli. So for technical content, some of the assumptions that we made were that the weight is evenly distributed between all wheels. This is a conservative assumption, as what we actually worked with was Caterpillar tracks. Therefore, the Caterpillar tracks would allow for better movement, and some of the torque that we calculated here is not exactly what we'll need. The actual DC motors that we acquired are 15 Newton meters, and theoretically, we were expected to use a 20 Newton meter torque for each motor. So these theoretical calculations, they did help validate a lot of our buying choices, especially the DC motors. And as Eli has mentioned, we did fry our module, but it was capable of moving its own weight. And we assumed in our technical calculations that it was at least 10 kilograms. As of now, it's probably a little bit less than that, but our technical content did uphold and did satisfy a lot of our design choices. Next would be going over the amount of expected regolith that we will bulldoze. Based on the cross-sectional area of the bulldozer blade, we were able, and the density of the regolith, we were able to calculate an expected mass that we would want to bulldoze. This is where the figure of 1.44 kilograms came into play. We expect in our testing, when we test to bulldoze a total distance of 1 foot, we expect to push at least 1.44 kilograms before we begin to experience some failure either in the tracks or probably some tipping or some sort. But however, we did choose the 1 foot distance for simplicity. We could probably go even further than that, and we can probably be able to move more regolith than theoretically calculated. And as far as for the structural design of this, we ensured that we wanted to follow the NASA standard 5001. This calls for a safety factor of at least greater than 1, and the engineering safety factor that we calculated at critical locations, such as the hinge location, we calculated a safety factor of 3.4. Therefore, we help validate more of our structural integrity to make sure that we won't fail at this critical location. And now I'll pass it on to Martin to talk about our project summary and conclusion. So for major accomplishments, I think the main accomplishment that we achieved is that we got it working and it was able to move through uneven terrain and it was able to push some sand. So just for the bulldozing operation, it was a success. It met the Lunabonics mass and volumes constraints. So by those standards, we should be able to still compete. Now, the shortcomings of the project is that it's not fully autonomous yet. Some of the 3D printed parts, we weren't able to have them ready for today's showcasing, which brings me to the next point, which manufacturing just takes longer than expected, which brings me to lessons learned, which I can't stress enough. Manufacturing just takes longer than expected, mainly because we had some complex geometries, and which we have simplified quite a bit, but we just ran into some trouble with the manufacturing phase of it. Another big lesson that we learned, as my colleagues mentioned here, is that we did fry some electronics, and we learned that it's very easy to fry electronics. And for future work, we want to expand on testing because we did test it, we got it to move, but we weren't able to gather any hard data on it, which is it's the next phase of testing that we want to do. And now, thank you everyone for coming, and I'll hand it off to Oscar just to speak about some acknowledgements.
We want to acknowledge USA Industries for our fabrication and manufacturing support. We also want to acknowledge our engineering manager, Armando Garza, and engineer Tang for design and technical guidance. And lastly, we want to acknowledge John Ray de Leon and Hector Davila for manufacturing support, as well as Claude Harper for technical analysis assistance. Thank you.
Time for one quick question.
I noticed one of the lessons learned was electronics fry easily. So I'm just curious, the array analysis on circuitry, just to make sure you were operating as performance.
We did consider it. One thing is that we definitely put our research in, maybe not as much as we, should have, but we did enough for it to get it working. I think that was our main goal, for it to start working. So one thing I did fail to mention, that we had it running perfectly fine, but we had to remove all the electronics. That way we can add one of the blades or one of the plates. And so once we had to remove those electronics, it basically messed up the whole system. So we had to start from scratch again. We thought that it was going to be the same thing, but unfortunately, sometimes things don't go our way. And well, we learned. That's part of the process, part of the learning process. And so we're still, I'm still tinkering with it. I'm still trying to understand it. We still have to purchase another motor driver for it. But to answer your question, we did do our research. We did, but again, there's always more room to grow, more room to learn about it. So.
Thank you. One more question. How do you communicate? I might have missed it, but how do you communicate with this vehicle? I didn't see any communications of any sort.
So the software, we didn't include the software, but it's Arduino provided a software, and it's used with C++ code, so it's autonomous. We should include it in our presentation, so thank you for bringing that up, but it is autonomous, so that's what's communicating to the robot.
All right, thank you, team. Okay, that marks the midpoint. Break time's over, come on over, grab a seat. We'll get started with the second half of our morning. All right, and first up for the second half are the Radcat Sentinels.
Good morning, ladies and gentlemen. We are the Radcat Sentinels. We come from Texas State, also referred to as the MIT of the South. I'm the project manager, Cameron Callahan. This is Noah Steres. This is John Camp, and unfortunately, our last member, Aaron Dahl, wasn't able to make it today. He's sick. Our project is a comprehensive validation suite for a RISC-V radiation-tolerant laptop. Why do electronics need to be radiation tolerant? Well, high energy particles come from the sun and space, and if they strike electronics, they can cause errors like flipping bits or even short circuiting the electronics. That's why we need a validation suite. What does a validation suite do? A validation suite is a set of tools used to ensure the functionality of the board. We use two tools specifically to validate the functionality of our board. That's the HSS and bare metal code. What the HSS does is it creates a list that goes through the initialization of required devices in the board on boot. What bare metal code is software that's written directly to hardware without the use of an operating system.
For the boot subsystem, before the board gets any power or anything, you need to boot the board before you can communicate with it, unless you're using the bare metal examples like he discussed before. However, to boot the board and get maybe an operating system on it, use the HSS. The HSS, you kind of think of it like a pilot before he gets on a plane. You're not going to fly the plane or take off before you check the plane, make sure everything's safe, everything's ready to function, ready to go. So there's kind of a checklist. It's the same with the board. Each peripheral will go through a checklist, and it'll let you know if it's okay before the board is fully booted. And if not, we put as many test functions, test points, so that it's super easy to debug, and it's maximizing how much we can test. The bare metal examples are essentially, like he said, it's before the operating system, and we have peripherals like the CPU, the RAMs, SD card, SPI flash, UART, and many more that are tested, and it kind of pokes at it, and it'll let you know if it's successfully communicated or if it's lacking communication, which once again makes for easy debugging and validation of the board.
Okay, the LCD click serves as the primary output device for our board, visual output. It works through bare metal examples or bare metal code. What happens is we code the processor directly. The processor then uses SPI to interface with the LCD click. And through that, we can program the LCD click to display stuff that helps us debug the board. SPI is just serial peripheral interface. That's just a communication protocol used by microprocessors to communicate with external devices. We also have a Wi-Fi module that operates in a similar way as the LCD click. We program the MSS directly or the microprocessor directly. The microprocessor then sends SPI signals to the Wi-Fi click module, allowing us to set up a wireless network connection.
For the PCI subsection, the PCI is actually embedded in a chip that is an FPGA chip. FPGA is a field programmable data array. Essentially what that means is most chips have circuitry hard embedded on it. An FPGA, you're allowed to manipulate the circuit through software with Verilog code, which is what Libero SoC is. So I was able to enable the PCIe through the binary device tree. The binary device tree is essentially a set of instructions for the board that runs through the peripherals during boot. So it's disabled when you first get the board. I was able to enable it and get communication through Linux. And then we're adding a M2 NVMe SSD, which is a solid state drive that allows for you to store certain whatever you want in there, and it also verifies functionality and of the lanes of the PCIe. The next one was the audio subsystem. Funny enough, it's not actually on the iSchool kit. However, it will be on the next iteration of this board that the effectively grounded team is working on. So they're implementing an I2S codec that will be controlled using an I2C. And I2S, it stands for a inter-IC sound system, which is very similar to an I2C, which is the inter-integrated circuit. They basically can connect different peripherals together. Just the I2S is basically only for audio. I created a mock Verilog code that makes a blinking light just to get practice and deeper understanding for programming the FPGA, so that when we get the I2S, which is in the FPGA, we'll be able to create a circuit and verify that the I2S is working on the next iteration on the board.
Good morning, everyone. This is the USB subsection. I was responsible for validating the 3 USB ports that are on the icicle kit. We did this by running the bare metal code that goes out, and like Noah was explaining, goes out and tests to see if it's receiving and sending signals. If it is, it prints a message for us. It lets us know. The 3 USB ports are pretty important on the incoming board that effectively grounded is going to be handed off to us eventually. One of them is used to communicate for the debugging. The other port is used for communicating with Linux, and the other port is what's called an on-to-go USB port. It's a little different than the normal USB, than your standard USB. Instead of having just your ground, your power, and your data in, data out, it also has a floating pin that allows you to configure it, whether you want it to be in host mode or if you want it to be in act like a peripheral. To do this on the icicle kit, you have to make sure that the pins for the V bus, that's the voltage that will be supplied to your peripheral through the port, is shorted as well as the ID pin that I was just mentioning. If these are shorted, then the board is in host mode, and you will be able to connect a USB device such as a keyboard or a mouse. That will be important to interface with the device once the OS is running. And then one of the methods that we use for debugging, there's a lot of examples that you can use for the bare metal codes. One of the ones that I used was the human interface device bare metal example, and that tests the mouse. It'll go and it'll make sure that it's there, and then it'll put it in a default state and put it into it'll say like top left corner or something like that. Anyway, I just pass it on.
Our accomplishments revolve around the HSS that was identifying and mapping the initialization of essential devices that are being initialized during our boot sequence. Here we have a bare metal example of us reaching out to the UART and making sure it's functioning without the use of an operating system. And our path forward is going to revolve around verifying the functionality of the main board that effectively grounded made and correcting any issues that might have happened. We would like to thank TSGC, our faculty at Texas State, Mr. Stevens and Mr. Welker, our microchip advisor, Jim Bogert, our D2 team Effectively Grounded, and our NASA mentor, Mr. Batista. Thank you.
Questions?
In your design, y'all said you were going to use an M.2 SSD, which is a completely digital form of storage. Wouldn't a hard drive disk be better to prevent bit flops and corruption of data?
Essentially, we are testing for that specific case. That was just to test communication to the PCIe. It's not necessarily what we're going to implement. we don't need to, what we're planning on doing originally was doing a USB hub. However, that doesn't really give you a great test for connectivity. But the M.2 NVMe has an adapter and then a SSD that shows solid proof that you're able to communicate to and from, which is really the main goal of it.
Another question?
Once your validation suite is complete and it's delivered to a customer, how long would it take for the suite to validate that the laptop is working or the chip's working?
Well, the validation suite isn't necessarily for the customer here. It's more to validate that the main board that effectively grounded makes is working so that we can then pass it off in the development phase to where we can change the form factor, add more peripherals that are, I guess, essential for interfacing with the laptop and just making sure that works. So the validation suite is really less mature in the line of development for the board.
To add on to that, like you were saying, it's hopefully once they get it, the customer shouldn't be having to validate the chip. So like you said, it's just for testing. However, the validation suite should work perfectly fine and they'll be able to access it ideally once they have a board to test.
I know y'all's others team wanted this to be a legacy project. What is it that y'all want to transfer to the next semester?
Well, next semester, we will hopefully have 2 people on developing the validation suite, continuing on that, and 2 people completing any hardware stuff with the board that hasn't been complete. And after that, we'll most likely continue iterating on the board with future teams coming in, like the juniors of this semester coming in next semester. They can be half on hardware, also half working on the validation suite until we have a fully functional proof of concept RISC-V laptop.
Yep. All right. Thank you, team.
One more. Sorry, really quick, but it's eventually going to be, if y'all guys have heard of the framework 16, it's essentially the laptop that we're kind of working towards form factor, like the form factor we're working towards.
Thank you.
Good morning, y'all. My name is Lathan. I am the team lead for the team Lunar Longhorns, representing the University of Texas, and I'm really excited to be here for y'all.
Hi, everyone. My name is Caesar, and a little bit about the background and objectives. So this project directly relates to NASA's Artemis mission, bringing astronauts back to space exploration on the moon. So it does this by allowing students to create a human-powered rover. This human-powered rover goes through a half-mile course made up of 10 different obstacles. To the right-hand side, you can see some of the obstacles, so different terrains, such like pebbles or like craters, for example. And this rover has some constraints. So it must be under 130 pounds of total weight, fit within a 5 by 5 by 5 foot volume box or 25 cubic feet, support the load of 2 riders, assemble, or it should be assembled in under 2 minutes, as well as having a 12-inch clearance off the ground.
Hi everybody, I'm Ryan and I'll give you a quick run through of our rover. So to start off, we have a triangular truss for our body. We have custom aluminum wheels, a independent suspension in the front, a tricycle setup, independent drivetrains in the front and rear, and back-to-back seating. Some of our top specs include 112 pounds of top weight, a length of 6 feet, and a width of 4 feet.
So I want to jump into the subsystem designs, starting with the frame. So whenever we're designing this, we're thinking about the effective weightness and how can we reduce the weight? How can we have a system that's able to hold the stresses and loads when actually driving a vehicle through lunar terrains and different off roads and stuff. The material that we landed on was aluminum 661 for on human powered rover, and we did a tricycle chassis design with 2 wheels in the front, 1 wheel in the rear, and that has a triangle frame based on influence through like bridge design and go-kart designs. And in order to be able to actually fit into the payload, which is like a 25 cubic feet rover, which would essentially simulate us sending it to the moon, we had to disassemble it. In order to do that, we decided to do a collar detachment system, which is, you can kind of see at the bottom right image, where it's split right in the middle. And we have 3-point collars that allow for it to sleeve over the existing tubes and have 2 holes for the threaded pin recognition to be able to pull in and put it back in during the driving in operation, and that way we can easily disassemble and reassemble in under 2 minutes.
Hi everyone, I'm Jalen, and for the drivetrain system, we used a design matrices to determine if we wanted a chain drive, a timing belt, or a shaft drive system. The 3 biggest factors that we took into consideration were the efficiency, the weight, and shock absorption. The efficiency and weight are very important because for the challenge, we're underneath a time constraint and also a weight constraint for the rover, as well as going over a lot of rocks calls for some shock absorption. So we decided to go with 2 independent chain drive systems. The person in the front will be pedaling forward and the person in the back will be pedaling backwards. Because the front has 2 wheels, we will have a U-joint that connects the driven shaft to the wheel. And additionally, since there will be a lot of dirt and debris in the course, we will have a chain guard to protect the system.
Thank you, Jay. All right, so the next thing we wanted to talk about is the steering system. So obviously, whenever you're driving a rover, that's quite important, and being able to have an operating vehicle that can turn at a radius under 10 feet and be able to actually maneuver pretty relatively easy is quite crucial. So what we decided to do was use Ackerman's steering mechanism, which uses a 3-point mechanism, 2 rods attached directly to the wheel hub assembly, with rods sticking up for you to steer, and a center rod connecting both of those to be able to access both powers, so you're not, independently forcing one of the wheels independently to rotate. This allows for rotation to be really easy whenever you're turning left or right, and the outer rim to actually be able to rotate at an easier level and not slip.
Hi everyone, I'm Max, and I'm going to talk to you guys about the brakes a little bit. So we started off looking at 4 different options. These were the mechanical disc, hydraulic disc, rim brakes, and stagecoach brakes. And we evaluated these using a Pew chart and looking at the wear, cost, integration, responsiveness, and reliability of these different systems. And overall, we ended up going with the mechanical disc brake. And you can see our custom design in the top right image there. There are longhorns cut out into it. And we are using that along with off-the-shelf calipers, cables, hubs, and brake levers, and a custom mounting system. And the brakes are mounted only to the front 2 wheels, so the front driver operates the brakes, and the left and right brakes are independent of one another.
So the next subsystem is the wheel assembly. So we have 2 main constraints. They must be non-pneumatic, meaning no air in them, and we need to make them ourselves, so self-fabricated, with the exception of being able to buy an off-the-shelf wheel bearing. So like on the left or the right-hand side, you can see that we mounted the wheel onto a double wishbone with suspension for the front, and the back has a bicycle centerpiece. So with this in mind, we had to fabricate the wheel, and the 3 main materials that we considered were aluminum, steel, and carbon fiber. So Steel, as you may know, may be very heavy, but it's ideal. However, since it is very heavy, we ended up not going with that. Another option we considered was carbon fiber. So carbon fiber is lightweight, however, it's very expensive and also very, very difficult to manufacture. So a good middle ground that we found was aluminum, specifically 6061 T6, since it balanced strength, durability, and terrain adaptability. And beyond just making the center piece aluminum, we also added a cosine tread design, as you may see, to navigate against the obstacle courses. This was inspired by previous iterations of past lunar rovers. And yeah, that's it for the wheel assembly.
So back to the suspension, main points I want to emphasize in the need of suspension are control and track performance. Believe it or not, you can traverse the track without a suspension and have it with a rigid bar. But if you do that, you wouldn't be able to properly conquer these obstacle courses, such as the incline on the top right. So this is what the wishbone suspension allows us to do. It gives us control, and you can see this clearly on the bottom right, where the left wheel is at a higher vertical distance than the right one, and this allows us to traverse undulating terrain and give us better track performance.
So looking forward into the future, given that this is usually a 2-semester project and we had 1 semester to complete it, we're hoping to pass our designs on to another team of UT engineering students, and hope that they'll follow through with a lot of our design choices. And then they would move into the manufacturing phase, and we estimate total cost to be just shy of $1,400. This would involve CNC milling and welding. From there, they would move into assembly and testing. Throughout the process, the drivers would be undergoing fitness training to make sure that they're ready to navigate the obstacle course.
Thank you. So one last thing, we want to thank all the advisors and teachers that helped us throughout the actual project at UT, also our NASA mentor, Mr. Salazar, and obviously Dr. Tim for setting this whole thing up. So, any questions?
Hello. Thanks for the presentation. The question is how quite smart having two astronauts looking in opposite directions, which will require some training, of course, but also how XMU friendly your design, with, especially with paddling. Imagine that you're in a pressure suit. How you consider it? Let's start from that point.
Sorry, can you repeat the part about the pedaling?
Well, because it's how you navigate it, right? So how you rover, use your rover around, right?
Yeah.
But imagine the astronauts are wearing XMU suits, right? EVA suits, pressurized suits. So how friendly is the design, including your pedals, seat, and everything?
Yeah. So part of the challenge for this one, and I forgot to mention this in the very beginning, so I apologize for that. But this is an entirely human-powered rover, so that part of the challenge is that you cannot have any like flywheels, any motors, or anything like that. So it has to be purely mechanical, human-powered. So ideally, we wouldn't be using a pedal system in outer space in a big suit because that's already inoperable. But in this competition, we had to use a pedal system. So that's kind of what we were kind of laying on. But yes. It's part of the problem that we're kind of facing. So, thank you for that.
I have 2 questions. You obviously have put some thought into assembly, the crew assembly of the system. You mentioned already that the students are, in this case, it's a student competition, so you have student drivers. But on a lunar operational consideration, we have a very difficult ambient lighting condition, whether it's straight dark or high contrast. And the operator, the astronauts would have to be assembling this potentially with just suit lights. So did you factor that into your connector design? I mean, maybe you didn't, but maybe that's something to think about the visibility of the connectors under not very good lighting systems.
Yeah, for sure. Yeah. So We actually didn't really incorporate that since it was, the terrain would be simulated on Earth and wouldn't be actually put out into outer space. So yes, and that was one of the constraints that we did. Another thing was like the weight and like the mounting. So we would probably incorporate that into future designs if we are gonna put on light on that. So definitely appreciate that input.
In this case, it was about the connector design and the crew being able to recognize parts of the connectors to assemble it, given they might have reduced visibility. The other question was, this is obviously just all mechanical, but have you thought about the idea of adding batteries or power systems on the vehicle in the event that they wanted to attach a lighting system onto the rover that's powered by self-power?
Yeah, so part of the actually constraints that were given for this entire project was there was no electrical system allowed on the system. Ideally, right, we would want to use an actual system that has electrical, some kind of power motor, battery, anything like that. But this is really like an over-engineered kind of like bicycle essentially, or like classic. So yeah, essentially, yeah, that's kind of where it is, where we're at. So yeah.
All right, I think we need to move on. So thank you, team.
Yeah, of course. Thank you.
Good morning, everyone. We hope you're having a great time. We are Keith Braden from the University of Texas at Tyler, and our project is a pH rotation model for astronaut usage. We call it the pH card. This is the slide showcasing the team members. I'm Christian Simmons, and I'm here with Agustin Garcia, Eduardo Gracia, and other kids. So let's get started with the background. Where and why is a prototype needed? For a bit more context, let's talk about life mechanics. So intravenous fluids are essentials for treating medical conditions that may arise during Mars missions, ensuring crew health and mission success. However, throwing enough IV fluids on board is impractical due to massive volume constraints and also the short shelf life. This is where the IBGM Mini project comes in. The project aims to solve this challenge by developing a compact, low-mass IV fluid generation device that can produce IV fluids on site. This will eliminate the need for launching and storing large quantities. The IBGen Mini builds on the original IBGen system developed by the Human Research Program Exploration Medical Capability Elements that successfully demonstrated the capability to produce IV fluids aboard the ISS in 2010. With those figures, you can appreciate both the original IBGen and the concept of the IBGen Mini system. Moving on to the next slide. What is it required then? A critical requirement for IV fluids produced by the IBGen Mini is meeting USP standards. This includes maintaining a pH between 4.5 and 7.0. Nonetheless, the IBGen Mini is expected to use the International Space Station potable water, which can be found at a range from 4.5 to 8.5 pH. This will create a risk of not meeting the USP standards for IV fluid saline solutions. And thus, to ensure compliance, our prototype must be able to read the pH of the input water before fluid generation. Our process statement is to develop a mini device with tubing and a data acquisition system that can monitor and regulate the pH levels of the potable water for astronaut use. Now, on to my next slide.
Good morning. So the question is, where are we going to connect our prototype? It will be connected right after the IV bag portable water of the IBGN Mini system, which is what it shows in this image. Next is the flow layout for the prototype. What you see there, it is the flow direction of the potable water. The main components to the sections are the pH sensor number 1, the main pump, and the check valve. Next section is the buffer solution. The main components for that section are the IV bag buffer solution, the dosing pump, and the check valve. Now, the buffer solution that we used was citric acid. The next section is the pH regulator, which is showing also the flow direction. A main components for that, it is the mixing junction, the flow meter, the air-free filter, and the pH sensor number 2, which is the final destination of our prototype. Next, we'll move on from CAD to prototype. So basically on your left-hand side, we see the design concept assembly and model. And on your right side is the prototype assembly that we created. Key components of these sections are the tanks and the pH sensors with the plus or minus accuracy of 0.1. The next is the IV bag. This is where the buffer solution will be stored. Next is the main pump and the dosage pump. Both the pumps were peristaltic pumps. And next is the mixing junction, a very critical component for our system. And finally, the air-free filter. Now, moving on to my class.
Good morning. I'll be discussing the pH guard functionality. So for the coding, we use C++ language, Arduino IDE software program for the components. So the goal for the code was to lower the pH of the output water. When the Arduino is turned on, it takes 10 seconds before it activates. It uses 2 pH sensors to measure the acidic levels at the input and output of a fluid stream and calculates the flow rate using a flow sensor. The data is processed and displayed on a real-time LCD screen, which shows the pH values and flow rate. Pump 1 starts at the system initialization and continuously runs for 4 minutes, while pump 2 is conditionally activated based on the pH values, first checking the input pH after 30 seconds, then adjusting based on the output pH every minute. The code takes about 4 minutes. Pass it on to my classmate.
Moving on to our results, since we're not using a physical mixer, we're just using that junction, we need to ensure mixing does occur at that junction. One main reason for this is that our pH sensors are actually fairly sensitive, and if a concentration of buffer solution is injected, it may throw out more readings. Figure on the left is our expected theoretical values, and the animation on the right is our experimental conditions. We saw an approximate 2.7% increase in our actual conditions, indicating to us that mixing is occurring more efficiently for our actual case. And here we have the results for our pH correction. We have 3 runs out of the total of 20 runs we performed. Initial pHs in each of our activation ranges, as well as 8.69, which falls above our expected range. One thing to note is that we stayed pretty consistent around 6.0 to 6.5 after correction, which falls within our USB standard of 4.5 to 7.0. One important note on this is that our operation time tended to be around 3 minutes and 30 seconds average across the 20, which falls below our maximum operation time of 5 minutes by 28%. And here we have the real-time pH correction for 2 cases. The first case in the gray starts off at around 8.69 that you saw previously, and you see that initial drop where that initial injection occurs. The second check shows that the pH is still out of range, and that's where you see that more gradual slope for the secondary injection. Case 2 starts around lower, around 7.4. That's where you see it just has that singular initial injection that is sufficient for its correction. One thing to note is that for our prototype, we're trying to mimic the function of the IVJet Mini, so some of the components aren't necessarily required for the prototype. So after analyzing components that could be removed, we actually are able to fit within our original dimensional specifications, as well as fall below our maximum mass specification by 12.9%. To conclude, we were able to successfully design, create, and test a pH regulation module that consistently lowers the pH of our potable water. By analyzing our required components, we did fall below our maximum mass constraint by 12.9%.
And by utilizing a mixing junction rather than a mixer, we're able to reduce our target time by 28%. We would like to thank TSGC for giving us the opportunity to work on this project, as well as Justin Yang and Dr. Mohammed Biswas for their continued support over these past 2 semesters. Thank you.
Questions?
Did you have to account for sensor calibration and sensor drift on the various sensors you're using? And how did you accommodate for that?
That is something we did have to, since mentioning the pH sensors, they are rather sensitive. When we initially started with our just individual component testing, it did take quite a while to keep our pH sensors calibrated properly. We have had to recalibrate them, I'd say two or three times over the just the semester, just to make sure they are staying consistent.
If we were to use the device on orbit, how would you calibrate in operation?
So to calibrate the pH sensor in ISS, first we will have to have more information about what type of pH sensors, if they're the same, they're going to use. If that's the case, it will fall between being industrial or digital pH sensors. The digitals tend to be more sensitive, so they will require more calibration. If it's an industrial, it will be a calibration recommended for every month. The way they need to calibrate it is using no pH solutions. And instead, we'll be using a 2-point calibration by using a 4.0 instead of 0 no solutions.
Another question? All right. Thank you, team.
Thank you.
So good morning, everyone. My name is Joseph Gibson, and I'm joined here today with Mr. Walker Sharp, Mr. Peter Bowling, and Mr. Matt Elator. Together, we are the Backyardigans, and today we'll be presenting over our soft goods attachment device. So here's a brief outline of the presentation. I'll be going over our product definition and background. So soft goods help provide thermal protection for sensitive equipment aboard the ISS to protect from thermal radiation from the sun. So in this picture on the right, all these white textiles on the outside are actually the soft goods with all the sensitive equipment behind that. So astronauts essentially need a tool to secure these soft goods to each other out in space. So here's a little breakdown of each of our textiles. They consist of 4 layers of mylar or emergency blanket, essentially sandwiched between 2 layers of X-Pack B21 material, which is essentially this tear-resistant material. So these are our soft goods textiles. Another word for it is MLI, which stands for multi-layered insulation, as we tell, multi-layered. So this is actually a picture of what we'll be testing our prototype on if selected for the neutral buoyancy test for micro G. If we assume everything in blue here on the left is the outside of the ISS, then we'll be working right here in the center that's zoomed in on the right. This blue dotted line is essentially where an astronaut has gone in, cut out some insulation, and either repaired or installed new equipment, and they now need a way to essentially patch back up that hole. So that's where our tool comes in. One of the big constraints you might have been able to tell is there's no way to reach around and get behind, as that's the entire ISS. So you can only access the front side of these panels. But to get a little bit more into these constraints, I'm going to go ahead and pass it on to Mr. Matt Latour for our project specifications and constraints.
Thank you, Joseph. And now that he just explained the scope of the project, though, I will discuss our product construction that were at the very from the key content design requirement for the newcomer version of Vico. And so just for the first five construction on this side, the sub edge. The first one is the sub edge must be remain 3 inches away from the 8 entry point star. The second one is the uncovered hole must be less than 0.5 inches or greater than 1.5 inches in diameter stuff. And the third one and the tools the tools 3D printing part must have at least a 75% infiltrate. And the fourth one, the ultimate tensile stress factor of the safety must be a greater than 2 with it. And the resistant and the tool must have a resistance to the bumping load with it though. And the next slide though, the last part for the construction though, the sixth one though, the tools must weigh under 10 pounds requirement, but it preferably have like less than 5 pounds with it though. The tools must have like on a deployment volume less than 1 feet volume though with it. And then like the eighth one though, the tools the tool destiny though must be a greater or just equal to the destiny to the 100 with it. And the tools a liner active force must be have less than 20 pound forces though, or just known as a 9 newtons though. And the last one though, the tools a rotation actor torque must have like less than 8 inches pound though, or just or no, it's like 3.4 newton meters though with it. And just as for the code standard though with it, it's with a mix of a mandatory NASA and a engineer institution standard though, just for our safety though with it, and pass it down to Pierre to talk about the concept designs.
Thank you, Matt. Last semester, our group focused on concept generation and preliminary analysis. With the aid of a pew chart, we decided to pursue a concept inspired by commercial tagging guns used for tagging clothes. This design works by puncturing the material with a hollow bore needle, allowing the user to drive one end of a tagging material through, leaving the other end on the original side, securing it in place. Our design is broken up into 2 main systems. The first system is the casing, is illustrated here. The casing houses all the internal components and takes the brunt of any experienced forces and the resultant stresses. The second system is the punching and tagging mechanism, primarily composed of a trigger and spring for actuation, a lever arm for translating motion, a slider and plunger for using that motion to drive tags, a magazine to retain and load the tags, and a needle collet for fixing the needle to the head of the tool. For our stress analysis, we applied a 30-pound force to the front face of the tool and examined critical points, in this case, where the handle meets the head of the tool itself, as shown here. We then calculated the resultant axial as well as bending moment stresses, resulting in using simplified geometry, resulting in a combined load of 970 psi. Seeing that the yield strength of tough PLA is 6,570 psi, this resulted in a safety factor of 6.7. Utilizing finite element analysis software, we verified our hand calculations by applying the same load to the front face of the gun while keeping the handle fixed. This resulted in a max stress of 779 psi at the point of interest, giving a safety factor of 8.4 and a percent difference of 19.7%. Considering our hand calculations use simplified geometry and assumptions, such as not accounting for applied fillets, this percent difference is reasonable. I'll go ahead and pass it on to Walker to discuss our testing procedures.
Thanks, Peter. Okay, so obviously after modeling and our preliminary analysis using finite element analysis and analytical testing, we manufactured our prototype. Then as soon as we manufactured our prototype, we had to start testing. First, we did functional testing, which we are reenacting back at our table if you saw us yesterday. Basically, we have 2 layers of MLI, and we're just puncturing it and then inserting the tag through it, making sure that the device operates as expected, which as you can see it did. It can do 2 tags back to back within our current magazine size. After that, we did a drop and bump test, just making sure that the tool can withstand small impact forces and then still operate as expected, which we can. Then we test our attachment security, see how much force we can exert on the tags before the 2 layers of MLI separate. Obviously, if we're doing this in actuality, the force will be multiplied by how many tags you insert within the MLI. So, and then also water submergence. If this tool was to be used in the microgravity test pools, we would want to see that the tool can operate the same in and out of the water, which it can. And then also the life cycle of the tool, which is something we're testing kind of currently, seeing how many cycles the tool can actuate before failure and which components will fail first. For future work, some pretty low-hanging fruit here. We want to increase the magazine capacity. It would be really easy to incorporate in our current design. Right now, the magazine holds 3, but just increasing the vertical distance of the magazine, we can add as many tags as we need, and it'll operate the same. But as for proof of concept, right now we have 3, and it can shoot those back to back. We also will definitely incorporate a collapsible needle sleeve. Prior to this, we didn't get a chance to add that in because of manufacturing time, but we will include that so that the needle isn't always exposed. It's only exposed when you puncture into the fabric. You can think of it like an EpiPen, kind of like syringe cover. We also want to increase the ergonomics of the gun, specifically tailored to the astronauts' EVA suits. So if we had some maybe some more insight onto how exactly they want the design to be and what dimensions they want shrunk or modified, we could adjust the ergonomics accordingly. We also want to manufacture new tag designs that you see on the right side here. Due to manufacturing limitations, we couldn't find a way to get a good enough resolution on a material flexible enough to incorporate this, but basically, instead of having a tag that is kind of like a I-shaped, we have a T-shaped tag with this tab on the end that would be able to have like an adjustable attachment length, and also would cover it would secure the outside of the hole that's left from us piercing the fabric. We also want to do further prototype testing to get some part numbers on our testing, especially life cycle, but also tag tensile tests. We want to see specifically the strength over the deformation of the tag and see what we can expose it to. Okay, so in conclusion, over the past year, we are trying to create a device that is very simple and easy to use and very reliable and only manually actuated, so we can have a cheap and easy to use device that that the astronauts wouldn't mind using in EVAs. Currently, we're in the testing stage and we're fine-tuning our design, but next we want to finalize our prototype, finalize and standardize our testing procedures, and then do it. Just keep iterating our design process to make sure we're finding the most efficient solution to this issue. And with that, that is the end of our presentation. I want to thank you all for listening, and we'll take any questions after.
You mentioned increase in ergonomics, and I was wondering what you factored into your design with respect to the EVA glove and its limitations.
So mainly, we wanted to make sure that the tool only had one variable for actuation. So that's why we just incorporated, like, the squeezing of the trigger, as opposed to having multiple tools do this function, which were other concepts we thought of. Also, how far the actuation goes. So we thought maybe the glove will have limited mobility from like here to here. So I would say that's, for me, I can clasp my fingers 4 inches. Maybe they could only do 1. So that's the travel of the gun has about like one inch of squeeze before you deposit the tag. And then also linear actuation force
on our gun, because it's kind of a rough prototype, I think that it's kind of hard to pull. For an astronaut glove, I would assume for a normal hand, it's pretty easy. But we could minimize that with like future iterations of the gun by just reducing friction within the method. So just force, the variables of actuation and the actuation like distance is the things we considered. But obviously like tailoring like the size and the handle of the gun, we don't really have the insight to do specifically. So we just made it comfortable to hold in our hand.
And then one more question, perhaps I missed it, but did you consider sharp edges in your design?
Yeah, we referenced the NASA like human integration standard to just see what they're calling, and also there's design requirements set out by Micro-G. They just talk about punch points and puncture risk, right? So that's why we're including the collapsible needle, but for right now, we're just kind of doing it as a proof of concept to see like what kind of solution we could come up with, but it's future work. We're definitely trying to make it safer. The collapsible needle basically would be a cylinder around or needle and collar would be like a cylinder around the needle that would retract within the device when you puncture the fabric. I don't know if that makes sense.
Yes. Thank you.
All right, thank you, team. All right, we will take another short break.
Thank you. Good afternoon, everyone. We are Team Artemis Owls from Rice University. I'm Pat, and I'm joined by my teammates Mac, Hanaro, William, Aga, and Favor. Imagine this. You're a NASA astronaut traversing the harsh terrain and environment of the lunar South Pole. And then something goes wrong. Your partner falls, injured. Time is ticking, and there's no lunar rover around to help. What do you do when an astronaut goes down during lunar EVA? The truth is, NASA doesn't yet have a solution for this scenario. Soteria is our solution. We've designed, tested, and built a rescue platform to safely retrieve and transport an incapacitated astronaut during EVA.
The rescue process for Soteria is as intuitive as it is life-saving. We've broken down the rescue process into 4 steps and consolidated it into an easy-to-memorize acronym, ENLIST. ENLIST stands for Extend, Lift, Secure, and Transport. First is Extend. The healthy astronaut goes to the handlebar, on which they can activate a lever, which mechanically unlocks telescoping legs. These legs are driven forward by motor-assisted front wheels, which drive the legs forward until the frame reaches a complete length of 7 feet, which is the maximum height of an astronaut. Next is lift. For this step, we have developed a long-handled tool which prevents the need for the astronaut to bend down, because in their spacesuit, their mobility is extremely limited. Bending down will be hard for them. The rescuing astronaut uses the magnetic end of this long-handled tool to connect the lifting arms carabiners onto the 4 attachment points of the new Axiom-designed spacesuits. 2 attachment points are on the shoulders and 2 attachment points are on the waist. Once the carabiners are connected, the rescuing astronaut cranks the winch, which gently and easily lifts the incapacitated astronaut up to the height of Soteria's net. All of this, once again, requires no bending, and there is no on-site assembly required. Next, we have the secure step. For this step, the rescuing astronaut will rotate around the long-handled tool to use the other end of it, which has a blunt hook. This blunt hook has 2 purposes. First, the rescuing astronaut uses the hook to extend the Soteria's net, Kevlar nets, under the incapacitated astronaut's life support pack. This provides essential upper body support. Second, the rescuing astronaut can use the blunt hook to hold the astronaut's legs and gently place them on Soteria's footrests. On the footrests are latches, which can be gently lowered with the blunt hook, and these lock the calves and ankles of the incapacitated astronaut in place. With the astronaut secured and stabilized, we move on to the final step, which is transport. The healthy crew member goes back to the handlebar to maneuver the ergonomic control panel. Our control panel is designed to give complete control of movement and speed to the rescuing astronauts. Once this is done, the astronauts make their way back to the lunar lander with a journey of under 2 kilometers. All of these steps are designed with the astronauts' limited range of motion in mind. The loading of the astronauts, or the extend, lift, and secure steps, can all be completed in just under 5 minutes.
So, to ensure a quick and efficient rescue process, our device features a control panel, a winch-based lifting arm, a Kevlar net, and leg rest as well. So we've engineered a Spartan chassis made out of T6 6061 aluminum. We chose a material for both its thermal performance as well as its high strength to weight ratio. This results in a total frame weight of 110 pounds. The base frame and its extended profile, this can span a length of 7 feet as well as a width of 4 feet and 7 inches. But for easier storage once in transport to the moon, the extended frame as well as hinges located both at the handlebar and at the lifting arm allow the frame volume to compact by as much as 60%. All of these design choices were put into mind to both minimize mass and volume. This way we can ensure cost effectiveness while still ensuring easy maneuverability.
We've also designed a dual-purpose assistant tool compatible with EVA gloves. One end of the tool has a blunt hook, which is used to raise the astronaut's legs without needing the healthy astronaut to bend over. This hook, thanks to a thread of attachment, can also be taken off and replaced with other EVA tools as needed. The other end of the tool has a magnetic attachment that we use to connect the astronaut to the lifting system. To connect the astronaut to our lifting system, we've designed custom carabiner housings that magnetically couple to our lifting tool. Once coupled, they can quickly be used to ensure fast and secure connection to the astronaut's built-in attachment points. Once the astronaut's attached, the winch does the heavy lifting. And once the astronaut is lifted, there's also ample room and clearance for the net to be extended underneath the astronaut's life support system and for the legs to be raised onto the footrest.
To meet NASA's requirement of transporting the incapacitated crew member a distance of 2 kilometers within an hour, we decided to fit Soteria with 350 watt DC motors at the front wheels paired with a 36-to-1 gearbox. This allows the device to reach speeds of up to 3.85 miles an hour, which is well over an astronaut's possible walking speed. So because of this, the motors are able to fully relieve the healthy crew member of all physical load during the journey back and allow easy traversal on inclines of up to 20 degrees. For safety and control, there's braking on all wheels to provide immediate stopping power on the rough lunar terrain. And after a lot of rigorous settlement calculations, we found that the Lunar rover vehicle wheels suffice for our needs and prevent the device from ever sinking into the regular. The system is operated by a thoughtfully designed control interface that has this enlarged UI form factor to account for the astronaut's large gloves. It has a joystick to provide differential steering on the wheels, a safety key tethered to the healthy crew member that acts as a reliable shutdown mechanism when it is detached, a display for system status and speed information, and finally a battery switch to toggle between main and rescue batteries to ensure operation throughout the entirety of EVA, which can last up to 12 hours.
In addition, we've conducted 30 trials on the lifting and secure portions of our process. On Earth, we're able to deploy in under 2 minutes. To translate this to the lunar conditions, we've calculated a scaling factor of 2.14 based on the ratio between lunar walking speeds and terrestrial walking speeds. Even then, our deployment time is to under 5 minutes, and a total rescue time of under 25 minutes. All of this is done by one crew member with no bending and no on-set assembly. For future directions, we've made accommodations to incorporate other purposes beyond rescue to our design. For example, we plan to incorporate storage space for EVA tools and samples. We plan to improve our mitigation against lunar regolith by incorporating bellows and having a fully enclosed motor system. Lastly, we plan to incorporate a radioactive battery to account for extended stay on the moon. Overall, we've designed, prototyped, and tested a fully functional rescue device to recover incapacitated astronauts back to their lander in a timely and safe manner. Soteria is lightweight, ergonomic, energy efficient, and above all, easy to operate, thanks to our enlist process. We are deeply grateful to our mentors, Anne Vaughn, Dr. Wood, Dr. Travis, as well as NASA TSGC and Rice OEDK for the continued support throughout our process. We thank you all for your attention and now welcome your questions on Soteria. As you might know, the South Pole, they're constructively created, their slopes up to 30 degrees. How would your design work with that?
Yeah, so that's a great question. So our design specification was able to traverse over 20-degree slopes, and so our motors are able to sufficiently cover that. And due to the high speed and the higher power of our motors based on the minimum power we calculated, our wheels would also be able to cover 30-degree slopes as well. I will also add that missions are designed such that the path that they would take would not enter those craters. Yes.
All right, so I noticed that you're using a CAD tool to come up with your planning. And one of the suggestions I have is that since you're using a CAD tool, that you use the light simulation option in the CAD tool to create the harsh solar environment shadowing, since the sun will be on a low inclination angle. My worry with all the small mechanisms on your design is that with the shadowing, they may not be as visible as you think they may be. So that was just a suggestion for improvement. And the only other thing is, like, again, the same tool, when you put the astronaut behind the cart, looking at visibility challenges the healthy astronaut's going to have in moving the cart.
That's a good addition.
All the controls on the control panel are shaped pretty differently, so all the controls can also be felt like tactile, and we assume that with training, the astronaut will also be able to, like, know which control belongs where. We also were not told of this constraint, but we believe that our design would be able to satisfy this problem, or we would be able to modify it appropriately as necessary.
So where on your design do the batteries power system go?
Yeah, so you guys will be able to check out our prototype at some point. It wasn't here yesterday, but our prototype is back there in the corner. And so we provided ample space beneath the handlebar, we mentioned it before as well, for both the toolbox and then also the batteries. So basically that whole empty area could be filled with, it's more than enough. I mean, if you take a look at our prototype, you'll see how small our batteries are compared to the space we have back there. So there's plenty of extra room to store batteries and other things.
Okay, I think we need to move on, but thank you, team.
Thank you.
So to give you an idea, our goal is to design and test two mobile robotic explorers capable of traversing the hypothesized surfaces of Earth and Psyche 16 asteroid in a future NASA mission. So focusing exclusively on mobility, our scope is to develop a robust system that can handle the uneven and treacherous terrain.
What is Psyche 16? It's an asteroid in the Milky Way asteroid belt, orbiting between Jupiter and Mars. It's metal rich, presumably a nickel iron core. This is important. This is important because NASA is still trying to understand how cores are created. And Earth's core has never been explored. Also, we still don't know how planets separate into layer structures. If this mission is successful, it would give us valuable insight on how Earth was created. Also, on October 2023, NASA launched an orbiter to do a preliminary study on 16 Psyche. Currently, NASA is still working on a lander for the future missions. Just to give you an idea of the atmospheric conditions, gravity, pressure, and temperature are very low when compared to Earth. The day cycle is 4 hours, and the orbit year is 5 Earth years.
So based on these atmospheric conditions, we developed the following specifications for our design. And so we want to keep it as lightweight as possible, considering the size of the asteroid as compared to other rovers on Mars and the Moon. So the mass, we designated a maximum of 40 kilograms and capabilities of carrying up to a 10 kilogram payload for any instrumentation for testing for solar sampling. The Explorer size limit, we wanted to keep it as small as possible to be able to ship it out there safely and economically. So we wanted to keep it under ADA standard regulations. And there were some, for the terrains, we considered surfaces that are smooth, gravel-like surfaces, boulders, as well as inclines. And so for those, we designated a climbability of up to 0.15 meters, stability on surfaces up to 30 degrees on an incline, and we wanted to keep the motion smooth and slow. So we designated a max speed of 3.2 kilometers per hour. So this is our concept that we developed. It's based off of the mechanical wheel configuration, and so each wheel is independently powered, and it allows for moving forward and backwards, as well as shifting side to side and diagonally, and conducting 0-degree turns on the spot. And this prevents having to do motions as in normal steering vehicles, where you have a turn radius. You avoid all those issues by turning on the spot. And we went even further to design it into a mode where it's able to remain fixed at one point and expand and serve sort of like legs in order to walk over larger obstacles. And here we have the closer look at the cab design. So the mechanical system consists of rollers angled at 45 degrees, which is what allows to shift from side to side. And in the final image, you see the expansion mechanism working. Here's our prototype of the wheel. As you see, on the right is the expanded view.
So designing an explorer to traverse the uneven surface of 16 Psyche asteroid presents several constraints. To address this, our explorer has an adaptive suspension system that can maintain balance by dynamically adjusting the center of mass. To give you an idea about the design, the two rocker arms on the side are connected by a link in the middle with 3 self-aligning bearings and 2 vertical stabilizing links in the rear to ensure that each wheel is able to keep an upright posture as the suspension system adapts to terrain unevenness. So basically what this does is this maximizes the tractive and climbing performance while allowing for damping without the need for springs. This system is powered by a 12-volt battery. It consists of 4 brushless motors controlled by 2 L298 control modules, which are responsible for wheel rotation, while we have 4 RC servos connected to a 16-channel PWM module installed for wheel transformation. For navigation, we'll be utilizing a Raspberry Pi camera module connected to a Raspberry Pi camera module, which is a compact high-resolution camera, ideal for navigation in small explorers analyzing different terrains. As you can see, by combining all these components and subsystems together, we were able to assemble a complete functioning prototype meeting all our specifications.
To meet our specifications and ensure the explorer performance capability, we were able to test it for different factors. We calculated our mass to be 30 kilograms. giving it a light well structure. The Explorer was successfully able to maintain the stability at 30 degrees tilting angle. The Explorer's dimensions were kept within the ADA compliances. The ground clearance of 0.15 meters allowed it to overcome uneven terrains, and our speed of 0.4 kilometers per hour kept the instruments on board and stable while moving.
So in conclusion, as far as the mobility aspect goes, we're able to complete the maneuvering around the different surfaces, including the inclines, the flat surfaces, the ridges, and the small obstacles, as well as the suspension system being able to mitigate major shaking and vibration of the bed. And we're still working on optimizing the AI camera system for hazard detection. But as far as mobility, we were able to conclude and meet all the specifications. And so we'd like to thank Dr. Bowman for her guidance from the NASA Psyche 16 mission, as well as thanking you guys for the opportunity to be here and participate in the conference. Thank you.
Questions?
So you have a lot of mechanisms with your wheels.
Yes.
And then one of my worries would be with that expansion contraction, plus all the mechanisms that will get gummed up with lunar dust. So do you have future plans to test how resilient your wheels are to a dirty environment?
So most of those things we considered it, but as far as the research goes right now, there's not really much clarity as what the terrain is like. So it could be solid surfaces, it could be gravel-like surfaces. So each of those would completely alter the outer structure of the wheel. So at this point, we wanted to go with something that is mostly for solid surfaces and capable of maneuvering in small levels of gravel, but not necessarily a fully like I guess like sand-like terrain.
Right.
One of the major concerns with low gravity, such as the asteroids, is how you secure your systems on the surface. Because whatever you do, so you can really be launched back in space. So traction is very important. Lightweight is important for you to deliver it, but on the surface, it's really not it's not a benefit. It's actually opposite. Do you consider working on that? How you secure your robotic system on the surface of an asteroid and moving it along the surface, not flying around?
So we did consider that constraint. So as of this moment, to address that, we kept our fulcrum point, basically our center of mass, right on the middle of the suspension. So it is easier for it to stabilize, in a low gravity environment. And the other aspect to address that constraint would be to keep the mass within the limits, so it doesn't react too much to low gravity environment.
All right, one more quick question. If not, all right, thank you, team.
Thank you.
I'd like to just, before we begin, request that any of the judges who are scoring this, wait till after lunch to grade ours. A little bit of a joke, but there's also some scientific evidence that might help us out here. So, hi, my name is Colin Peters. I'm the project manager for Team Lights Camera Bobcats. This is my teammate Keith Griffin and my teammate Jonah Hartley. And we put together an integrated camera and lighting system to support manned and unmanned exploration missions on the moon's surface. So you'll see this lovely picture of our moon, courtesy of the wonderful folks at NASA. And it looks a little bit different than what we're used to because that's a time exposure of the lunar south pole. So you see some areas around craters that are light, which indicate that there are areas that are in near constant sunlight and some craters that are constantly dark. And this all presents a very interesting high contrast environment where the moon is characterized by an incredible range between the lit surfaces and the dark surfaces on a scale of like 120 dB. I mean, it's a really large difference. And so it presents a unique challenge from a lighting condition. So we really had to sit down and dream up a good solution for it. And Jonah is going to talk a little bit about that.
Thank you, Colin. Our solution focuses on three main goals: granularity, redundancy, and mission safety. Some of the features we implemented to support these goals are multiple light sources, including spotlights and floodlights at both high and low angles, a vertical array configuration that allows us to assign lights to different distances, thermal management solutions to each of the systems within our project, emergency power and battery tracking capabilities, manual mode that allows astronauts to override the computer, fully automatic mode that will illuminate shadows without user input, as well as 2 HD cameras specialized for day and nighttime operation. The first phase of our project was the lights phase, where we defined, drew, and dreamed many different solutions to our problem. We focused on finding a grid of lights that best supports our main goals. By drawing sector maps and assigning lights to different sectors, we were able to draw different solutions to fit our individual main goals. This figure on the left is a sector map for our design that focused on granularity. By taking the main features of each of these designs, we were able to create a final design whose sector map is seen on the right. This design supports granularity by allowing us to illuminate our 4 outermost sectors individually using high-angle spotlights. This design also supports redundancy and therefore mission safety through the use of low-angle spotlights and floodlights that ensure that each sector has at least 2 lights able to illuminate it. Once we had a design that we liked, we were able to move on to the next phase of our project.
During the camera phase of our project, this is when we started realizing our dream and turning it into a reality. We did a lot of researching into the nitty-gritty details of our project, everything from wire sizes to what components we were going to use, what camera would work best during daytime or lunar days and lunar nights. We drew up circuit diagrams and circuit simulators and ran them to make sure that they would work before we tested them on real components. And we drew this all up and we put all of our information in a project specification document, which we have linked as a QR code at the end of the slide, as well as on our poster board if you want more information on that. But since we don't have the time to go into all the nitty-gritty details, and brief overview of what our project is, we have a power system that also runs as an emergency backup system that runs our Pi 5, our camera, and all of our other components. And if in case of main power failure, our system will continue to run. Our Pi 5 takes images from the environment by the help of one of our cameras, analyzes the lighting conditions on it, and then sends an appropriate signal to each of our lights in order to light each sector that we want to light up accordingly. During this process, we had a lot of problems with, we also had to resource all of our components, which was one of the biggest challenges of this project. A lot of our parts we wanted to use for the project that we found and desired weren't even our first or second choice is what we ended up getting, because they were either too costly, they wouldn't come until after the semester was over, or they were from a provider that wasn't approved for us to be able to buy from. So there were some components we had to get, like the IMX462 camera, which we thought would work because it said it was Pi camera supported, but ended up not working with the libraries that our other cameras use, which made integrating the system very difficult to do. But we were able to find a better camera and eventually replaced it with that. The biggest lesson that we learned during this phase was that preparation is key. We put a lot of work planning before we started building everything, and that saved us a lot of time, and we wouldn't have been able to get it as far as we have in this semester if we didn't plan as much as we did. There was an Abe Lincoln quote that we had, and that kind of inspired the beginning of the process. You know, give me 6 hours to chop down a tree, I'll take the first 4 hours to sharpen the axe. And that's what we've done.
And it really paid dividends for the next phase, which is the Bobcats phase. That's at Texas State, what we like to associate with action. That's building, testing, and if we broke it, we tried again. So we had so many huge deliverables during this period that we had to put together. We had to do the electronics and the drive boards. We had to wire up the heatsink, put together the frame, etc., test all of those subsystems, and then do a full system integration to build our showcase product. Along the way, I mean, we had challenge after challenge. So for instance, sending clock signals over long lengths of wire, it acts like a transmission line, and you see smearing across it because of the capacitive effects of the wire. In order to combat that, we had to change the clock speeds and troubleshoot something that worked for our system. Overall, the wiring was incredibly complicated. We ended up having to choose both a DIN rail and a DIN plug that we assembled ourselves in order to manage everything. That saved our lives during the troubleshooting. We had, you know, the serial peripheral interface pins that we were using on the Pi 5. We had a random blowout on them that was unexplained, and we had to change the master bus. You know, we tried to troubleshoot that and couldn't find the cause of what had happened. It never happened again. Our Pi, after hundreds of tests, has always worked fine. So it was just something we had to adjust the bus and move on. We also had weird ground bounce and noise issues where our system was shutting off, the ground plane of our boards was rising, and it was driving these clear pins low, and we had to bleed out high frequency noise with some capacitors. Overall, and then, you know, the trouble didn't stop there. We also had to down select. We wanted to use higher rated 50-watt resistors that could dissipate more heat because our circuit relies on feedback resistors to develop a sense voltage, and those get very hot because they see a lot of current. That's part of what we want to focus on for our future plans. Is right now, if you look at our system design, we have a very large over-spec heatsink, and we want to take an individual solution, a heat solution for each component, and build something that will fit inside of our enclosure completely. And we learned just so much along the way. And even though I said these were all challenges, these were really all learning opportunities. You know, one of the biggest things we learned is, here it's written, don't leave things floating, but it's really that we live in a world that's cause and effect. We were doing something that's a little silly, which was when testing our amplifiers in the beginning, we weren't providing it with a voltage, mistakenly assuming that no input is a volt or an input that's equal to 0 volts. That's not true at all. And as a matter of fact, it can cost you some components. I would encourage the team that had problems with their own, you know, Arduino board, I believe for the dozer bot, hook it up to a scope and remember this, that since we live in a world of cause and effect, we can use one of the greatest tools, which is the scientific method. You can observe, hypothesize, and experiment, and if you can't fix it, you can try again. We're Lights, Camera, Bobcats. Thank you very much.
So I know for this challenge, the previous solution took into account the fact that the lights would reflect on the astronaut's helmet and it's difficult to see it. Is there any sort of solution included in this sort of, maybe so the lights are not always too blinding if they're pointed directly where the astronauts are?
You mean for if the astronaut is directly in front of the enclosure looking in?
Yeah, like under the spotlights, for example.
For that, right now we don't have a system implemented in that would exactly monitor a astronaut or a figure. You could, if you were very, very concerned about that, I could say that you could, you know, possibly look into training a model that could decide, you know, what is a human shape or what's an astronaut shape. You could also use sensors as well. You could have some sort of maybe a Bluetooth sensor that communicates the position of where the astronaut is relative to the central processing system. You know, if it's oriented in a direction, you could look into stuff like that. That's a really interesting problem. And it's something for the scope of our project. We haven't implemented a direct solution for that, but I think that there's a lot of really cool ways to solve that. Thank you, that's a great question.
Any other questions?
As far as lighting is concerned, were you operating with any sort of power constraints?
For power constraints, so we did not have a specific power constraint that we thought was a limiting factor for us, because we chose, frankly, a solution that's relatively power inefficient. We chose to not do pulse width modulation because pulse width modulation, which is the current standard for LEDs here on Earth, it can lead to video capture problems. You can have moiré patterns appear, etc. So part of our working assumption for the project was that we were choosing something that traded off in one aspect, it was a little bit more power efficient, but offered, we thought, a lot of other pluses. You know, for instance, that it's a problem that is not a point of redundancy within a computer system, so it makes it possible for people to troubleshoot it on the fly. I mean, if I could fix it in a lab, I know that we could have astronauts fix it out in the field. And there's a lot of other benefits to doing a linear drive system as well. But we didn't have any specific power constraints that we were focused on. We did calculate out, you know, information about the power and the consumption, which my teammate Jonah maybe can speak to, but we weren't operating under a ceiling. Do you want to add to that at all?
Sure. The main consideration we had with power is we want our entire circuit to be surge protected. We didn't want a surge on the last day to ruin our project. So the main power consideration is we had to make sure that the power draw from our entire system was properly rated for the device we used for surge protection.
All right. Sorry, just as it's all, you know, running, it's you know, under slightly the assumption, you know, is in this environment, like we said, it's lit 90% of the time by sunlight. So we were working relatively under the assumption that being able to source energy in this area was not our priority. I'm not saying it is not important and not a priority at all. It definitely is. But for the scope of our project, we did not choose to prioritize that aspect. Thank you.
All right, thank you, Bobcats.
Thank you. Good morning, everyone. That's right, it's still morning, but I promise lunch is coming soon. Judges, we're not worried about psychology, so please feel free to grade us at whatever point in time you would like. We're Team Pleiades from Texas Women's University presenting mitigation and muscle atrophy during long-duration spaceflight. I'm Anaya Kashiker, and these are my teammates, Martha Inahosa, Matthew Pearson, and Clay Martin. We'd like to thank our faculty mentor, Dr. Rigby, and our NASA mentor, Dr. Reyna. In the fall, Team Pleiades presented Hypertrophic Aid by Limb Occlusion, or HALO, to mitigate muscle atrophy in spaceflight. The HALO utilized a cuff-like device to occlude blood flow to an extremity by applying pressure to major arteries. Overall, the HALO was effective in providing a necessary physiological stimulus to elicit muscle growth. Here's Martha to speak on the background of our project. Gravity plays an important role in eliciting stress on our postural and weight-bearing skeletal muscles, such as the quadriceps, gastrocnemius, and soleus, to help us perform everyday movements. In microgravity, disused and unloaded skeletal muscle atrophies up to 20% in the first 5 to 11 days of spaceflight, therefore negatively affecting performance during mission tasks. To enhance the benefits of exercise, BFR, or blood flow restriction, is used to occlude blood flow to a targeted body segment by using a cuff-shaped device to apply pressure to arteries. When using BFR, a light intensity is used to perform up to 75 repetitions across 4 sets. This method will elicit similar responses as high-intensity resistance training. This low-intensity training with BFR lowers the risk for overexertion, decreases muscle injury, promotes muscle hypertrophy, and aids in muscle recovery. Another complementary technique that can be used during exercise is neuromuscular electrical stimulation, which elicits muscle contraction by delivering electrical currents through surface electrodes placed on the muscle belly. With this stimulation, fast twitch muscle fibers, blood circulation, and reinnervation are increased, therefore improving overall musculoskeletal health. The problem faced this semester with this information was the deleterious effects of spaceflight on muscle function. Our solution was to create a compact blood flow restriction device that integrates neuromuscular electrical stimulation to be implemented with resistance exercise prescriptions during spaceflight. Our device is called the Pleiades, or pressurized limb occlusion with electrical stimulation integration for attenuating the deleterious effects of spaceflight. Here is Matthew to explain our device.
The blood flow restriction system uses an Adafruit Metro and a motor shield to control 4 DC motors and a pressure sensor. The system is powered by a 3.7-volt battery and USB plug-in. The air bladder is placed inside the cuff and is attached to the motors and valve via silicone tubing. Together, these components work to inflate and deflate the BFR device. The system is programmed to inflate to a target pressure range of 100 to 105 millimeters of mercury. When inflation is triggered, the motors run until the cuff reaches the target pressure. If pressure drops below range, the motors turn back on. If it rises above range, the motors shut off. The system maintains this target pressure range automatically. Therefore, this creates a hands-free, self-regulating system that ensures consistent pressure control for safe and effective training. The neuromuscular electrical stimulation system uses an Arduino Uno to control a MOSFET, which acts as a switch for the electrical pulses sent to the electrodes. Power comes from a 3.7-volt battery, which is amplified by a DC-DC booster module. The voltage, and therefore the intensity of stimulation, can be adjusted using the manual potentiometer on the booster to match individual needs or muscle groups. The Uno is programmed to send electrical currents lasting 350 microseconds at a frequency of 45 hertz. These rapid pulses are delivered for 1 second, followed by 2 seconds of rest. This cycle is designed to stimulate the target muscles during the concentric phase of an exercise, while allowing for rest during the eccentric and isometric phases. A push button toggles the system on and off, and a pull-down resistor prevents any false signals from triggering the stimulation. This repeatable stimulation pattern provides a time-controlled neuromuscular response for consistent and effective activation. Here's Clay to summarize our testing protocol.
Focus on the cuff as it inflates with the pressure numbers increase. And focus on the cuff as it deflates with the pressure numbers decrease. And here you can see neuromuscular electrical stimulation working, evidenced by the change in EMG waveform. For testing, baseline measurements were taken after a 7-day period in which a young female participant abstained from exercise, alcohol, and caffeine. Baseline measurements consisted of blood marker concentration, maximum torque output, and 1 repetition maximum of 5 key exercises of Romanian deadlift, back squat, deadlift, single leg heel raise, and single leg knee extension. 7 days later, exercise testing using blood flow restriction was tested, with 25% of 1 repetition maximum across 75 reps across 4 sets, with inclusion pressure set to 100 millimeters of mercury. Blood draws were then taken 2 hours post-exercise. 7 days later, exercise testing with the addition of neuromuscular electrical stimulation was added, with hertz of 45 hertz and 350 microseconds. Blood draws were taken 2 hours post-exercise, and maximum torque output was taken 72 hours post-exercise. For blood marker concentration, vascular endothelial growth factor, or VEGF, was tested. This helps elicit angiogenesis, which is the formation of blood vessels. This helps increase circulation, bringing blood flow, oxygen, and nutrients to the muscles to help recover and grow. Additionally, blood flow helps reduce arterial stiffness, which is a common concern for astronauts. As seen on the screen, VEGF increased noticeably after using the Pleiades device.
For measuring maximum torque output using a isokinetic dynamometer, the Pleiades device the participant increased noticeably after using the Pleiades device. And here's Anaya to talk about our fall improvements.
The team has made several design improvements since last semester. The most notable was the addition of electrical stimulation to further promote the benefits of low-intensity resistance exercise with blood flow restriction. Next, the cuff was redesigned with a thicker and more rigid nylon fabric, with internal stiffeners to maintain shape while inflated, and additional Velcro placement to maximize adjustability. The air bladder was handcrafted with PVC plastic, using an iron to create seals along the edges to improve sustainability. The code was also updated to maintain pressure in the air bladder by reading when the value drops below a target value. This turns the motors back on until the target value is reached. Finally, we expanded our testing design with the use of an isokinetic dynamometer to measure maximum torque output. For our future directions, we would like to improve user-friendliness and accessibility with additional buttons or dials to control occlusion pressure and stimulation frequency. We would also like to improve and optimize our electrical stimulation parameters to enhance the comfort of our user. These include amplitude, pulse width, and stimulation frequency. In conclusion, the Pleiades device, which elicits blood flow restriction and neuromuscular electrical stimulation, can be used to enhance skeletal muscle adaptations during long duration spaceflight with resistance exercise. Thank you to everyone who helped us this semester. You can scan the QR code to see our list of references. Thank you so much for listening to our presentation, and we are happy to answer any questions at this time.
How do you know that your testing protocol is like the one that shows that your device is the most effective? Like, does it match conditions in space? And especially with only one test subject, how do you account for like other things they could be doing throughout the day that may have contributed to this rise in the DGF?
That's a good question. So the exercise that we picked, the 5 exercises, those are ones that astronauts are already doing in space with the giant ARED for lower limb muscle strength. And then you asked about how we know that our device works in terms of VEGF. Well, as you can see, when we took blood draw concentrations, we picked times, which was 2-hour post-exercise, where VEGF is said to peak after exercise. So that's why you see 2-hour post with BFR only, and then 2-hour post with the Pleiades device. You can see that even just with one participant, it's a noticeable difference. Obviously, if we had the time and the resources, we would have liked to recruit more people, maybe even males. It's a little bit hard at Texas Women's University to find participants that are not gym bros. So that would be a future direction for us.
I want to ask about VGM because I don't understand it, but for the max torque output, for the baseline, are you also doing the 25% 1 rep max sets to measure that before measuring that baseline? Like, are you doing those exercises for her?
At the baseline testing. So baseline, we took a 1 repetition max test. So we actually followed the American College of Sports Medicine guidelines for 1 repetition max testing, which means how much you can lift for 1 exercise 1 time. And so we did this with every single exercise with the 5 exercises. And then we measured maximum torque output just to see what the participant's initial torque was.
So I guess like I asked because like what's stopping us from rationalizing that it was her previous exercises that improved the torque output?
We actually recruited a participant that was considered inactive, so she hadn't been exercising.
But then she might have like UV gains where she's.
That's true.
A lot of the time.
Yeah, you see an increase in muscle strength pretty quickly in the 4 to 6 weeks once you start exercise. And so again, if we had more time and more resources, we'd have liked to draw out our testing period.
We also had a washout period of 7 days between to avoid a training response effect as like that NIMBY effect, trying to mitigate that with the time constraint that we had in order to test our device as well.
I suffered a knee injury a couple of years ago, and I had an extensive PT for my leg. I also had muscle atrophy.
I use both of these devices excessively, and I think my question is, if there are already commercialized solutions, why not just send them to the ISS? And the second question would be, the research that you did is great, but the studies have already been done, so I'm just curious about the gaps that you maybe addressed in your own research. Thank you.
Thanks for your question. We were looking at specifically long duration space flights. So we were told that to assume that the spacecraft that's being sent to Mars is like a minivan size with 4 people with prioritizing high oxygen, water, and food, and mission critical equipment. They don't have room for a giant treadmill. They don't have room for a giant exercise machine like they do on the ISS. And so our device is a compact combination of BFR and NMES.
All right, thank you very much, team.
Thank you. Enjoy that.
All right, that concludes our morning. We're up to our lunch break. You're going to have about an hour and a half to go see the posters, see the models. I encourage you to go visit